It is not a single instant, not a neat photograph in a textbook, but a long, angry stanza of motion and heat. 4.5 billion years ago, the whole thing began as a question scribbled in the dark margins of the cosmos. A whisper of dust and gas, a cloud so vast that human minds struggle to hold the scale. That whisper was the solar nebula, a diffuse, spinning fog where chemistry and gravity argued over who would shape the future. From that argument, a planet would emerge. At first, the nebula seemed indecisive. Tiny grains of silicate and metal drifted in the slow currents of a protoplanetary disk, brushed by radiation and nudged by faint electrical attractions. The encounter between two specks was not cinematic in any familiar sense, it was patient and relentless. A grain would stick to a grain would gather a film of ice, then another, then a pebble. Over thousands of years, those pebbles became rocks, and those rocks became boulders. The process was not graceful. It was a grinding crescendo of contact and collision in which every hit registered as a new chapter in a growing object's life. Gravity, indifferent and inevitable, took over where adhesion could not. As mass concentrated, its pull became a new force in the neighborhood. A small clump, heavier than its surroundings, began to shepherd nearby material. Others rose to the same task. 1,000 centers of attraction competed in a crowded dance. In the dim light of a nascent star, chaotic orbits intersected. Collisions exploded with energies incomprehensible on human scales, glancing blows that chipped surfaces, head-on plunges that vaporized volumes of rock. This was accretion, a chaotic construction site where the architecture was brute impact. Each collision was a miniature apocalypse. Imagine a body hundreds of kilometers across, a protoplanet, meeting another of similar size. For an instant, the kinetic energy locked in their motion converted into heat, so intense that surfaces melted and vapor rose like steam from an enormous pot. Plumes of molten rock and metal unfurled into space, incandescent fragments were thrown into new trajectories. Some of this debris escaped into the void, some fell back in cascades, and some remained, suspended in a circumplanetary halo. In such episodes, the young Earth gathered its mass the only way a world could, by swallowing and being reshaped by the shrapnel of creation. As mass accumulated, the internal story of the growing planet changed. The continual bombardment combined with the slow squeeze of gravity heated the interior. Radioactive isotopes, products of older generations of stars, decayed, releasing their stored energy. Melt formed at depth, and a critical transformation began: differentiation. Heavy elements, principally iron and nickel, succumbed to gravity's inexorable sorting. They sank toward the center, not with intention but with inevitability, forming a dense core. Lighter silicates floated upward, forming a viscous mantle. This segregation was the planet defining its bones. The formation of a metallic core was more than a structural detail, it was the inception of something that would later protect and in time nurture life. The motion of the molten metal, stirred by rotation and heat, would eventually set up a dynamo, a magnetic field encircling the world like an invisible shield. In those first eons, though, the core's creation was a violent choreography of sinking iron and rising rock, of molten rivers and convecting layers. The surface was no calm plain. It was a blistering, incandescent ocean, a magma sea tens to hundreds of kilometers deep, beating and cooling in fits and starts. Sometimes, the most decisive blows came from a single, exceptional event with the force to rewrite destiny. The leading hypothesis for the moon's origin posits such an event, a Mars-sized body, later called Theia, collided with the proto-Earth in an impact so catastrophic that it tore away a great mass of material. In the aftermath, a ring of debris formed around the surviving Earth. Within this orbiting detritus, the Moon coalesced. The scene is often dramatized as an instantaneous cataclysm, but the reality was a complex, drawn-out settling. Debris clumped and reaccreted, heat radiated, and the angular momentum of the Earth. Moon system was forever altered. The collision tilted the planet's axis and contributed to the rhythms of seasons and the stability of climate millions of years hence. It also stripped, scattered, and reformed the early crust. Another reset in a long series of geological edits. After such titanic encounters, the young Earth was not calm. The surface remained molten or semi-molten for extended periods. Large impacts would resurface broad swaths, setting off shock waves that churned the mantle, induced pervasive melting, and lofted dusty veils that dimmed light. In those moments, the term surface itself became fuzzy. Where solid crust briefly formed, it could be turned under in the next great collision. It is jarring to reconcile the image of a tranquil blue planet from space with this primal furnace. An early Earth that was red, glowing, and raw, punctuated by incandescent plumes and flash-burnt craters. The fires were not merely destructive, they were creative engines. Volcanic activity, driven by pervasive heat, expelled gases trapped in the crust and released by melting. Water vapor, carbon dioxide, nitrogen, and traces of other compounds. These outgassed volatiles swelled into an early atmosphere, thick and steam-laden. But this atmosphere was unlike the one familiar today. It was dense, heavy with greenhouse agents, and opaque with suspended ash from planet-spanning eruptions. Sunlight reached the surface through a haze, and the balance of heating and cooling dictated whether the molten skin would give way to pools of liquid or stubbornly cling to vapor. Time, the slow overseer, watched as the planet radiated heat into space and as the magma ocean began, imperceptibly, to cool. Cooling was not uniform. The first solids to appear were likely high-temperature minerals, forming a patchwork of floating crustal plates that drifted and collided. Pockets of the mantle crystallized, dense materials sank further, contributing to the ever-maturing stratigraphy of the planet's interior. Islands of solid crust rose like the first islands in a sea of fire, transient in their infancy but crucial as anchors for later complexity. Water's role in this emerging story was ambiguous and decisive. Some water condensed directly from the steam-dense atmosphere as the surface cooled. Other water arrived later, delivered by comets and hydrated asteroids whose icy interiors survived long enough to deliver their cargo upon impact. These deliveries, intermittent and violent, could flash boil on arrival, but they also added to the growing reservoirs of liquid when conditions allowed. Pools and shallow seas would emerge in low basins, alternately evaporating and refilling through cycles driven by impact heating and volcanic outgassing. Protection for these fragile beginnings depended on the developing magnetic field. As the iron core convected and rotated, a magnetic shield would coalesce, deflecting charged particles from the young sun and mitigating some of the stripping effects of solar wind. Without this nascent dynamo, much of the atmosphere might have been stripped away early, as likely happened to nearby Mars. The dichotomy is stark, subtle differences in mass and timing. How quickly the core formed, whether the dynamo switched on early enough, determined whether a planet could hold on to its blanket of air and, eventually, water. The physics of tiny particles and the timing of colossal impacts became a delicate choreography with outsized consequences. Even as these physical processes unfolded, the solar system itself was not a placid nursery. countless bodies continued to wander chaotic orbits, some crossing paths with the nascent Earth. The late heavy bombardment, a proposed epoch of intensified impacts, left its marks in craters and in the memories preserved in ancient rocks. Each impact was a narrative interruption, sterilizing heat, searing shock waves, and yet also delivery of new materials. The pace of life's preconditions was not linear or guaranteed. It wandered through cycles of destruction and restoration, pause and renewal. The early Earth, then, was a paradoxical theatre, where obliteration and creation were two faces of the same essential movement. Beyond the mechanical, there is a human response to this story, a sense of vertigo at the scales involved, a feeling of smallness before processes so vast. It is easy to think of beginnings as tidy instants, an origin myth with a single author. But the birth of Earth resists tidy explanation. It was iterative, contingent on randomness, and yet obeying strict laws of physics. Gravity was impersonal, heat was indifferent, yet between them, under their influence, a world formed that would, through a long sequence of accidents and persistences, become hospitable. The first rocks that lingered from those fiery times offer faint testimonies. Zircons, tiny and hardy minerals, preserve chemical whispers that hint at liquid water existing on the planet's surface earlier than might be suspected. Isotopic ratios in ancient samples speak of early crustal recycling, of material being melted and remade. Those geological messages are fragmentary and coded, requiring patient decoding, but they anchor the imaginary theatre of early Earth in measurable reality. They remind observers that though the narrative can be phrased in grand metaphors, it is also a series of verifiable steps, collisions, melts, segregations, condensations, each leaving traces that patiently await human interpretation. To stand at the edge of this narrative is to accept a particular temperament of awe. The formation of Earth did not promise a future of life. It offered only possibilities within a brutal and indifferent physical landscape. Yet those possibilities, once set in motion, a stable orbit, a protective magnetic field, a steady supply of volatiles, intermittent calm after fury, would conspire over an unimaginably long sequence of trials to make room for chemistry that could self-organize into more complex patterns. This is why the violent beginning matters. It was not an incidental prologue to a softer story. It was the crucible that forged the conditions necessary for everything that followed. The collisions that scorched and the melts that rearranged left a planet with a differentiated interior, a dynamic surface, and the capacity to retain an atmosphere and water. The moon-bearing impact adjusted the tilt of the planet, influencing the cycles of climate. The core's birth set the stage for a magnetic shield that would guard fragile molecules from stellar fury. Without those brutal first chapters, the later pages describing oceans, continents, and life might never have been written. And yet, beneath the scientific register, there is a philosophical afterimage. The early Earth's birthing screams, measured in impacts and degrees, Kelvin, invite a reflection on the contingency of existence. What appears stable, a blue marble hanging in silence, is the result of a long and violent negotiation. Fragility and endurance are not opposites here, but neighbors. Small differences in timing, magnitude, and luck could have yielded a very different world. An arid rock stripped of atmosphere, a ball of ice, a lifeless ember. Instead, through a sequence of brutal but generative events, a world emerged capable of hosting the restless experiment that would be called life. So when the narrative reaches the end of its first chapter, when the magma ocean begins to cool, when the first persistent crust forms, when the atmosphere thickens and moderates, it does not mark a gentle victory. It marks a pause, a suture in a still ongoing process. The Earth's birth had been violent, as the phrase implies. It was also astonishingly fecund. In that violent beginning, chaos folded into form, and a world was assembled capable of memory, of geology that would later record epochs, and of complexity that, much later still, would look back and try to tell the story of its own origin. The question returns, what does the birth of a planet feel like? For the planet itself, feeling is a category reserved for later epochs. For humans, the story induces a trembling recognition that everything deemed permanent is perched atop a history of catastrophic making. The Earth's infancy was a litany of collisions, heat and reformation, violent and relentless. But it was within that litany that the conditions for future wonders were first struck. In the silent aftermath of cooling, the world lay bruised and new, a place of possibilities, waiting for the slow chemistry and the patient accidents that would, in time, produce the first fragrant hints of life. What does it mean for a planet to be molten? Imagine asking not about surface weather or seasons, but about the physical state of the world itself, the bones of a planet liquefied and singing with heat. That image is not poetic embellishment, it is the literal condition of Earth in its earliest millions of years. The molten world was not a gentle cradle, but an unending theatre of violent, incandescent processes. It was a place where chemistry and physics contended in visible, catastrophic gestures, where rock behaved like water, where heavy metal flowed like oil, and where the very notion of ground was provisional. In those first epochs, the planet's exterior was measured in thousands of degrees. Temperatures at the surface and in the upper layers of the mantle were high enough to melt silicates. Whole regions of the globe existed as a magma ocean. This molten skin was not uniform. It thinned and thickened, surged and congealed, formed ephemeral crustal plates and then tore them apart. Imagine waves of glowing rock, tens or hundreds of kilometers deep, sloshing and convecting. These were not waves of liquid water, but rivers of molten mineral, their flow governed by viscosity and gravity, their motion punctuated by explosive outgassing and colossal impacts. The story of heavy elements sinking is central to this molten epoch. Iron and nickel, denser than the silicate melt that surrounded them, began an inexorable migration toward the center. This was not a calm settling, but a convulsive rearrangement. Metal droplets coalesced, merged into blobs, and cascaded downward through the viscous mantle. In the turbulence of a magma ocean, these metal rafts pierced through convective currents like meteorites through fog. Each descent released latent heat and contributed to the convective churning that defined the planet's thermal evolution. The segregation of metals established the fundamental stratigraphy of the planet, a metallic core encased by a silicate shell. That stratigraphy would, in time, change everything. The nascent core was a crucible for electromagnetic drama. As iron accumulated and reorganized, it did not simply sit. The combination of rotation, convective motion, and the peculiar properties of molten metal set up electric currents. Those currents, in turn, generated a magnetic field, at first chaotic, then, as patterns stabilized, a more coherent shield. This early dynamo was patchy and fickle, but even a nascent magnetic cocoon could tilt the odds. It offered partial resistance to the young sun's particle wind. Without such a shield, much of the atmosphere, the very volatile inventory that might one day host oceans, could have been stripped away. The presence or absence, the timing and strength of this dynastic magnetic field were subtle planetary variables with outsized consequences. Below the visual spectacle of glowing oceans and sinking metal, chemical transformations were underway. As the magma ocean cooled and began to crystallize, minerals separated by density and composition. The earliest solids were refractory minerals, those that cool at higher temperatures, and they floated or sank depending on their buoyancy relative to the surrounding melt. Fractional crystallization created chemical layering in the mantle, sequestering certain elements at specific depths. Crucially, elements that liked to bond with iron, the so-called siderophiles, were largely drawn into the core. That left the silicate shell depleted in these metals and enriched in others, shaping the geochemical canvas from which future crusts and, eventually, any chemistry of life would arise. This differentiation had a practical after effect. The remaining mantle and crust became reservoirs for incompatible elements, those that do not easily join solid minerals and hence concentrate in melts and residual liquids. These elements would later be important carriers of volatiles and of catalytic metals, setting the stage for diverse mineralogy and a more complex surface chemistry. In short, the molten separation rearranged the planet's periodic table, making some atoms plentiful in the outer layer and hiding others deep in the core, where they would be invisible to surface processes. Outgassing ran in parallel. Under the pressure of the interior's heat, volatile compounds trapped in minerals or delivered by later impacts were released into the growing atmosphere. Water vapor billowed out in vast quantities, along with carbon dioxide, nitrogen, sulfur-bearing gases, and lesser species. Volcanoes were not isolated peaks, but vast, continuous belts of eruption, fissures that released plumes high into the emergent atmosphere. The pale, steam-laden sky was dense and reflective, thick with aerosols and ash. Sunlight, already diminished in intensity compared to what it would later be, filtered through a grey haze. Thermal gradients between day and night meant winds of prodigious ferocity. The atmosphere and magma ocean were in conversation. One shaded and insulated the other, while the other replenished and reshaped the first. Cooling, however, was not linear or inevitable. The magma ocean released heat to space, but every large impact, every surge of volcanism, and every redistribution of mass could reset local or even global conditions. The surface might form a thin, crystalline crust, a skin of solidified basalt and more refractory minerals, only for a later collision to flick it off like ice from a pot. These cycles of freeze and remelt were more than cosmetic. They drove chemical exchanges between the surface and the interior. Where solid crust persisted, it behaved like skin on a boiling cauldron, brittle, fragmented, and in places able to support transient pools of liquid, islands of relative stability amid the relentless movement. The first crustal fragments were not continents in any modern sense. They were transient rafts and plates of different composition, sometimes buoyant and sometimes dense. Where less dense felsic material formed, proto-continental blocks could float longer, acting as scaffolds for chemical concentration. Where darker, denser basalt formed, it tended to founder and recycle into the mantle. These early cycles were the proto-tectonics of Earth. Primitive mechanisms of crustal creation and destruction that would, over eons, evolve into the plate tectonics recognized today. Even then, these processes were crucial for long-term climate regulation. The sequestration and release of carbon through crustal mechanics would later act as a planetary thermostat. Water's arrival and behavior in this environment were paradoxical and decisive. Under a steam-choked sky, water could not simply pool and remain. It condensed in episodes where local cooling allowed, only to be evaporated again by reheating. Yet water also existed as a component of minerals and as ice locked in bodies that later impacted the planet. The delivery of water by icy planetesimals and comets was messy and intermittent. Many of those objects disintegrated on contact, their ices vaporizing in a flash of steam. But water is resilient in aggregate. over tens of millions of years. As the planet slowly shed heat and as impact rates declined, more stable reservoirs of liquid water could accumulate in low regions. Where lava met vapor, dramatic interactions ensued. Molten rock contact with steam generated explosive phreatomagmatic eruptions, throwing glassy shards and creating unique mineralogical textures. Where molten rock met early shallow ponds or seas, rapid quenching produced pillow lavas and glassy margins, signatures that would, in later epochs, be read as evidence of water-rock interaction. One of the less obvious but profound consequences of the molten epoch was the generation of chemical disequilibria. The dynamic interface between hot, reducing interior and an oxidizing, volatile-laden surface created gradients, thermodynamic imbalances that are essential for driving complex chemistry. Hydrothermal systems, where seawater or condensed steam seeped into hot rock and emerged altered, produced mineral-rich plumes abundant in heat and chemical potential. These plumes carried reduced compounds like hydrogen and methane, juxtaposed against oxidized seawater, a chemical battery. Over geologic timescales, such disequilibria are the raw energetic currency that can power synthesis and complexity. The molten earth, through its leftovers, vents, altered crust, mineral interfaces, produced innumerable such batteries across its surface and seafloor. The molten world was also a theatre of extremes in time. Short, violent episodes, impact flashes, eruptive paroxysms, mantle overturns, occurred against a backdrop of slow, patient processes. Core cooling, gradual compositional evolution, the steady decline in volatile flux. This combination of scales is what created both volatility and eventual stability. A planet that cooled too rapidly or that remained molten for too long could have followed very different trajectories. The timing of core formation, the pace at which the magnetic dynamo stabilized, the chronology of volatile delivery, each was a variable that could tilt the future toward retention or loss of atmosphere, toward lush hydrospheres or desiccated rock. There is tension in that thought. The molten world was brutal in its physics, yet delicate in its outcomes. Small differences in the timing or magnitude of events had outsized consequences. On a planetary scale, contingency reigned. Would the dynamo persist long enough to protect an atmosphere? Would the first crustal islands survive the next giant impact? Could water delivered by comets find a basin deep and cool enough to remain? These were not rhetorical questions for the planet. They were determinative forks in its evolutionary path. The molten epoch left signatures that modern scientists can read like a palimpsest. Isotopic ratios in ancient minerals whisper of early differentiation. The distribution of siderophile elements hints at the degree and timing of core formation. The textures of ancient zircons, tiny, resilient time capsules, contain evidence that pockets of cooler, wet conditions emerged earlier than might be expected in a uniformly molten world. These geological relics are fragmentary but indispensable. They transform speculative narrative into constrained, testable history. They are the fingerprints of a world that spent its youth in fire. And yet, for all the violence and heat, there was a quiet, philosophical subtext. The molten world teaches a particular lesson about emergence. Complexity does not arise from calm. It arises from energy flow, from concentration, from boundary conditions and gradients. The intense conditions that melted the planet and rearranged its elements were not mere obliteration. They were the preconditions for later structuring. The sinking iron that produced a core also created the magnetic shield, The outgassing that thickened the atmosphere also provided the molecules that condensed into oceans. The convective churn that kept the planet molten also mixed and distributed the chemical ingredients necessary for future innovations. When the magma ocean finally gave way to more persistent solid crust, when the steam atmosphere thinned enough for liquid water to persist in places, when the magnetic field steadied and the rate of sterilizing bombardment declined, the Earth did not become suddenly hospitable. Rather, it crossed thresholds, subtle, cumulative transitions that allowed localized pockets of relative calm and chemical richness to persist. Those pockets were the seeds of later complexity. They did not guarantee life or civilization, but they made the chemical theatre in which such possibilities could be rehearsed. In the molten world, then, one sees both the cruelty and the generosity of planetary processes. It was a crucible in which elements were sorted and energies concentrated. It was a time of loss and of securing. Metals disappeared into the core even as the atmosphere thickened. Crustal fragments were destroyed even as persistent chemistry became established. The molten epoch was not the end of a story, but the setting of conditions for a complex, slow, uncertain future. The long game of a planet learning, through heat and flux, how to hold and process the materials and energies that would, much later, support a world we recognize. Could a single collision decide the fate of a world? Could one moment, a violent rearrangement of mass and momentum, write the conditions that would later allow oceans to linger, seasons to stabilize, and a magnetic heart to beat? The hypothesis that a Mars-sized body, later called Theia, slammed into the young Earth is less a dramatic anecdote than a hinge in a long, messy narrative. It is a question about contingency writ large. How much of a planet's future is encoded in one catastrophic encounter? The scene that scientists reconstruct is cinematic in scale, yet stubbornly complex in detail. Theia would not have been a tiny pebble, it was a planetary embryo, comparable in mass to Mars, traveling a path determined by the chaotic choreography of the infant solar system. Its approach was dictated by gravity and chance, by subtle orbital nudges and the lingering dynamism of protoplanetary debris. When the two bodies met, the collision was not gentle. Kinetic energy, the energy of motion accumulated over orbital lifetimes, manifested as heat, shock, and instantaneous reshaping. For an instant, that is infinitesimally short on geological timescales, the planet they were became something else. The sky at that time could not be called a sky in any comfortable sense. It was a roiling sea of vaporized rock and suspended ash, thick with silicate clouds and toxic gases. Sunlight, if it reached the surface at all, did so filtered and reddened like light through a smoky lens. This was the atmosphere of a planet still being formed, dense with steam and volatiles, fouled by ejecta and chemically far from the air modern organisms would recognize. Into this opaque, angry vault, Theia plunged. The impact released an amount of energy that strains ordinary language. It melted rock in enormous volumes, vaporized crust, sent shockwaves pounding through the mantle, and launched a vast ring of debris into orbit. Where the two bodies met, temperatures spiked to tens of thousands of degrees, material vaporized and formed a transient envelope of superheated gas. Some of that gas escaped into space, but much of it condensed into droplets and particles that would rain back down or remain in orbit. The immediate effect was a wholesale reshuffling of mass. Crustal fragments were stripped away, mantle plumes were stirred, and iron-rich cores, those heavy, dense hearts that had begun to form, were jostled and merged. That merging is crucial. Prior to the collision, Earth was already differentiating. Heavy elements were sinking toward the center, forming an incipient metallic core within a convecting mantle. Theia, too, if it were large enough, would have had its own iron core. The impact likely forced the cores to interact violently. Streams of molten metal could have been stripped out, mixed, and ultimately incorporated into a larger, more consolidated central core. This event, more than any earlier accretionary collision, had the potential to add substantial iron to the growing planetary heart. It was not just a reshuffling of surface rocks, it was a redefinition of the planet's interior architecture. The dynamics of molten metal in that instant were both simple in principle and fiendishly complex in practice. Denser iron and nickel sank through silicate melt with the inexorable pull of gravity, but the extreme turbulence of the post-impact environment meant descent pathways braided and folded, droplets coalesced into streams, and the whole process fed heat back into the mantle. The resulting core became warmer, perhaps more chemically heterogeneous, and significantly influenced the convective patterns that would govern magnetic behavior for eons. In other words, the collision was a catalyst for the dynamo, the process by which a spinning, convecting metallic core generates a magnetic field. But the magnetic story is not a single, simple switch. The newly augmented core may have restarted or intensified convective motions by suddenly altering thermal gradients and composition. The addition of Theia's iron, the heating from the impact, and the redistribution of angular momentum could combine to set up a more vigorous dynamo. A stronger, more coherent magnetic field would better shield the atmosphere from the solar wind, enabling a planet to hold on to volatiles. The timing mattered. If the dynamo coalesced soon enough after the impact, it could protect the atmosphere during a delicate recovery period. If it lagged, more of the atmosphere might have been stripped away, altering the trajectory of surface cooling and the retention of water. The collision thus operated on two levels at once: an external reconfiguration, the formation of a debris ring from which the Moon would later form, and an internal reconfiguration, the consolidation and heating of the metal core that would become the planet's shield. The Moon's birth, in this hypothesis, was the debris' second act. The impact launched a circumplanetary swarm of molten and solid fragments. Some of that material achieved escape velocity and was lost. Much remained in orbit as a dense, incandescent disk. Over time, months, years, perhaps tens of thousands of years on astronomical timescales, that disk cooled, clumped, and accreted into a singular body. The Moon, a companion born from the planet's wounded debris, would carry the geological fingerprints of the collision. Isotopic similarities that suggest material exchange, a mass distribution reflecting the violence of its origin. But beyond its geology, the Moon would affect Earth's rotational stability, promoting the tilt that gives seasons and dampening certain chaotic variations in spin. The collision did not only deliver material to orbit, it introduced a new cadence to the planet's motions. The immediate aftermath on the surface was apocalyptic in human terms. Temperatures soared locally and globally. Molten oceans lapped higher. Incandescent rain of molten rock and glass. Spherules pelted the newly reworked crust. Basins formed by the impact and subsequent collapse. Scars that, in some modern analogues, can be many thousands of kilometers across, left the planet's exterior pocked and restructured. The air, already heavy with steam and volcanic gases, thickened with vaporized rock. In this vast, choking sky, chemical reactions accelerated. Silicates and metals that in calmer times would have stayed locked in the lithosphere were present as vapors, reacting with other volatiles in a volatile chemical stew. It is revealing to consider the timescales that followed. The immediate collision was over in a cosmic heartbeat, but the restoration and re-equilibration took far longer. Debris settled into orbit, and accreted into the moon over thousands of years. Heat radiated into space over millions. The newly reorganized mantle convected and burned for perhaps tens of millions of years more. These were epochs in which the surface could swing between molten seas and temporary crustal patches that would be remelted by later impacts or by the planet's own internal convulsions. The magnetic dynamo, even if invigorated, would take time to stabilize into a pattern that reliably shielded the atmosphere. There were losses as well as gains. The impact likely stripped a portion of the atmosphere and any pre-existing volatile reservoir. Much of the surface water present in steam or shallow pools would have been driven into vapor, and some potentially lost to space in the immediate fury. But the process also created new pathways for volatile delivery and retention. Outgassing from a reworked mantle and the recondensation of vapor in cooler niches over time gave the atmosphere another chance to rebuild. The planetary inventory of water and gases was thus neither simply preserved nor wholly destroyed. It was remixed and redistributed in a way that would determine where water could persist once the planet's fever broke. Within the mantle, the shock waves and overturning flows triggered chemical and thermal rearrangements whose consequences unfolded over millions of years. Mantle plumes generated by the impact's thermal input could alter melting regimes and volcanic patterns, producing extensive basaltic resurfacing and creating new styles of crust. These resurfacing events would effectively reset the mineralogical clock in many regions, burying earlier records and forging new crust that would later be sampled by impactors and, if life appeared, by the chemistry of nascent environments. The impact's angular momentum transfer mattered too. It altered Earth's rotation rate and axial tilt in ways that would have long-lasting climatic consequences. A faster or slower spin changes day length and atmospheric circulation. A different tilt changes the distribution of sunlight across latitudes and the amplitude of seasons. The program of weather and climate that would follow over hundreds of millions of years had at some level been rehearsed in the fraction of a moment when Theia met Earth. What appears in the rocks is the residue of these processes. Isotopic similarities between lunar and terrestrial materials point toward a common origin, siderophile element. Concentrations hint at the degree to which metallic cores mixed and resegregated. Tiny glassy spherules in ancient strata, shocked minerals, and megabreccias speak of high-energy melting and rapid cooling. The evidence is patchy, sometimes ambivalent, but persistent voices in the geological record align with the idea that a cataclysmic impact re-sculpted both the visible and the invisible architecture of the planet. Philosophically, the giant impact is a stark illustration of contingency on planetary scales. Here was an event that was neither inevitability nor insignificance. It was not guaranteed in the sense that Earth's formation logically required a Mars-sized collision at a particular time. Rather, it was one of many possible outcomes in a chaotic accretionary environment. Yet once it occurred, it altered probabilities in profound ways. It thickened the core's inventory of iron. It supplied the raw material and orbital geometry for a large moon. It redefined atmospheric inventories, and it remixed the planet's geochemical trajectories. Small changes in the angle, speed, or mass of the impactor could have produced a very different world, one with a different rotational rhetoric, one with a subdued dynamo, one with less capacity to hold an atmosphere. The present Earth, with oceans, seasons, a protective magnetic field, and a solitary moon, is in part the outcome of that single immense collision. The giant impact is not an endpoint, but a transformation. It was a violent passage from one configuration to another, from a crowded, chaotic disk of protoplanetary fragments to a planet-moon system whose subsequent evolution would include the pause and play of cooling, reaccretion, and volatile stabilization. The scene leaves a moral for those who study deep time, that planetary identity is not something slowly accreted and steadily refined in uniform steps, but is rather the product of episodic, sometimes abrupt, edits. Thea's strike was one of those edits, decisive, destructive, and creative all at once. We're looking back across the vast archive of geological time. The image that remains is of a planet that was remade while the sky itself was a toxic sea of vapor and ash. It is humbling to recognize that the magnetic shield later generated by movements of iron in that reconfigured core might owe its existence in part to that cataclysm. From a narrative perspective, the giant impact becomes a dramatic inflection point, an event that, despite its brutality, helped to assemble the conditions for long-term stability and the eventual emergence of environments where chemistry could try more complicated experiments. It was not destiny, it was chance reshaped into consequence. What does quiet mean after an unforgettable roar? What does the world do when the violence that shaped it finally loosens its grip and, for the first time in a long time, waits? The question hangs in the air like a suspended particle of glass. Fragile, crystalline, impossible to ignore. In the long drama that began with collisions and incandescent upheavals, the next act was not another explosion, but a retreat. Cooling down. It was a slow unmaking of fury into form, a patient folding of heat into structure that would, in time, allow mystery to gather and endure. The aftermath of the giant collision was not a single tidy epilogue. It was an architecture of cooling measured in millions of years, a choreography of solidifying minerals and erupting fire. Immediately following the strike that cast mountains of molten debris into orbit and birthed a satellite, the planet was an urn of heat. The upper layers had been vaporized or molten to tremendous depths. The sky was thick with silicate vapor and steam. The dayside temperature was a furnace. But heat leaks into space. Radiation, the unsparing accountant of energetic systems, began to take its toll. The incandescent veil dimmed slowly. As it did, the planet passed through a sequence of thresholds, each one an invisible gate that allowed new kinds of stability to exist. Solidification began at the margins. In the cold darkness of space, the outermost skin of the magma ocean began to crystallize. High-temperature minerals, those that condense at the highest energies, were the first to emerge. They formed a brittle armor, a patchwork crust that floated upon still liquid layers below. These first crustal pans were fragile, often ephemeral. They collided, welded, and sank again, tossed by the convective churn beneath. Yet these early scabs were not unimportant. They provided the first places where chemical gradients could persist, where pockets of cooler fluid chemistry could develop, and where novel mineral assemblages could take root. The process was messy and local. In some regions, the crust thickened faster, buoyed by compositions that resisted foundering. In other places, dense basaltic flows, products of rampant volcanism, sank back into the interior, recycling both heat and chemistry. The result was heterogeneity, a global skin that was not uniform but a mosaic of nascent plates, protocontinents, and transient ocean basins. The idea of a continent or stable sea floor was still a future possibility. At this stage, those concepts were provisional experiments in the planet's emerging geology. Lava did not vanish when the world started to cool. If anything, its activity became more articulate. Rather than existing as a global, homogeneous sea, molten rock found paths and outlets. Fissure eruptions and massive flood basalts reshaped large regions, burying older surfaces and creating new chemical canvases. Volcanoes were not solitary cones, but great belts and curtain-like eruptions that expelled heat and volatiles to the atmosphere. Each eruption was both a manifestation of interior heat loss and a chemical injection into the young atmosphere. Carbon dioxide, sulfur compounds, nitrogen, and vast quantities of water vapor. The atmosphere responded in turn, thickening and changing its optical character, acting as both a blanket and a reflector. Water's behavior during this cooling drama was paradoxical and decisive. Steam dominated the air for a long time, stubborn in its refusal to condense under a sky choked with aerosols and the radiant heat of a still warm surface. Yet cooling happened in fits and margins. Nights were long and severe, shadows on the planet could fall into pockets cold enough to coax condensation from the vapor-heavy sky. Where local cooling found purchase, in shielded basins in deep impact created depressions at high latitudes, droplets could form, collect, and linger long enough to begin to carve mineral boundaries. These pockets were transient at first, flash flooded by return impacts or scoured by eruptions, but they were also the crucibles where liquid chemistry could begin to take a more patient form. Time, here, is not a single slow line, but a tapestry of overlapping rhythms. Radiation to space proceeds relentlessly, but internal convection is capricious. A large, late impact could reset a significant region to near molten conditions. Meanwhile, smaller, persistent eruptions continue to leak heat and volatiles, steadily altering atmospheric composition. Over a span of millions to tens of millions of years, a cumulative effect emerged. The steam-dominated sky thinned in places, and the first stable bodies of liquid water could survive for geologically significant periods. Pools became ponds, ponds merged into shallow seas. In depressions insulated by stable crust, water could remain long enough to participate in complex chemistry rather than being returned immediately to vapor. The Moon, born of the debris ring, exerted its influence during these same cooling centuries. Tidal forces, once chaotic and strong, acted as a persistent mechanical hand. In shallow seas and molten margins, tidal flexing generated heat and mixed water bodies, increased erosion in coastal zones, and drove currents that redistributed sediments. Importantly, the presence of a relatively large satellite introduced a stabilizing torque on the planet's axial tilt. Prior to the collision, Earth's axis could have swung wildly under the gravitational whispers of other bodies. The new configuration dampened those swings. Axial tilt, once fickle, acquired a more consistent inclination. That steady tilt was the seed of seasons, reliable variations in sunlight distribution across latitudes that, in time, would govern climates and biological rhythms. Yet seasons did not spring into existence as a neat calendar. The tilt altered the energy input across the globe, but the response was filtered by atmosphere, ocean, and distribution of land and sea. In the cooled but still young Earth, seasons were extremes. Periods of relative warmth contrasted with times of severe chill, modulated by the planet's still developing heat transport mechanisms. Weather systems were ferocious. A dense atmosphere carrying volcanic aerosols could trap heat at lower layers while shading the surface, causing complex thermal gradients. Storms were fierce, driven by dramatic contrasts in temperature between sunlit and shadowed regions. Even so, the emergence of a consistent axial tilt introduced a repeatable cadence to the planet's insolation patterns, an important scaffold for any later seasonal chemistry and ecology. Beneath the superficial drama, the interior continued to evolve in ways less visible but no less consequential. The iron core, newly augmented and reorganized by the giant impact, cooled and convected. Molten metal in the deep interior did not simply rest. Its motion generated electric currents, which in turn produced an invisible magnetic cocoon. At first, this dynamo was capricious, fluctuating as thermal and compositional gradients settled into enduring patterns. But as epochs passed and heat flux settled, the dynamo found a steadier beat. This magnetic shield, though intangible, mattered profoundly. It deflected charged particles from the young sun, reducing atmospheric sputtering and helping the planet retain volatile envelopes. In a cosmic sense, it was the slow, quiet workman that allowed fragile molecular experiments on the surface to survive the erosive attention of space. The process of crustal maturation was equally gradual and intermittent. Where early crust persisted, chemical differentiation proceeded. Weathering, limited at first but locally significant, began to act upon rocks, breaking them down into fine-grained sediments carried by ephemeral streams to low-lying basins. Hydrothermal systems, where seawater or condensed steam percolated into hot rock and returned enriched with chemicals, became hotspots of redox chemistry. Those systems did not make life, but they made concentrated chemical gradients, batteries of potential energy that later, if conditions permitted, could be harnessed into increasingly complex chemistry. Black smokers and alkaline vents in later epochs would be the heirs of these early hydrothermal forges. The cooling Earth also began to archive its own story. Solid crust could preserve records, layers of volcanic ash, sequences of cooled lavas, chemical signatures from altered minerals. Impact basins became repositories for ejecta and sediments, preserving a stratigraphy that, millennia later, could be read by those who would study deep time. But preservation was partial. Erosion, burial, and subsequent melting erased many early chapters. The geological record from this phase is fragmentary, a palimpsest of survival and loss. What remains is precious precisely because it is scarce. There is a moral. To the cooling, stability, and fragility are two sides of the same coin. The planet's transition from widespread melt to a world with a solid crust, persistent volcanism, an atmosphere thick with volatiles, nascent oceans, tidal influence from a youthful moon, and an emerging magnetic shield created overlapping regimes of possibility. These were necessary but not sufficient conditions for the later proliferation of complex phenomena. The stages of cooling, an interplay of heat loss, continued internal dynamism, and episodic external shocks made pockets of stability possible. In those pockets, long-duration chemical experiments could proceed without being immediately sterilized by fire or vacuum. Across these millions of years, the narrative of cooling is also a narrative of listening, the planet learning to speak in new registers. Where once the language had been exclusively heat and impact, it began to include rhythm, the slow pulse of tides, the cycle of condensation and evaporation, the seasonal beat imposed by axial tilt. These rhythms allowed repetition, and repetition allows accumulation. Complex sequences require time and repetition to become more than ephemeral accidents. Cooling provided both. To stand in imagination at the boundary between molten fury and the first patient crust is to feel both consolation and unease. Consolation because the world was moving from chaos to a kind of ordered differentiation that allows continuity, unease because the order was fragile and would always be subject to reset. The Earth's capacity for storing memory, in rocks, in isotopes, in the geometry of its orbit and tilt, was being established in these cooling chapters. But memory can be overwritten. Later impacts, tectonic recycling, and volcanic resurfacing would blur, distort, and sometimes erase these earliest inscriptions. And yet the simple fact of a cooling is quietly electrifying. It implies permissiveness. It implies the possibility that, somewhere in a shallow tidal pool or around a heat-steeped vent, molecules might find the patience to combine into longer sequences, to form polymers, to explore the possibilities of self-maintained chemistry. Cooling did not guarantee such a trajectory, it only made it possible. In the hush, after the planetary screen, the stage was being set. The story of cooling is therefore an invitation to humility. Deep time operates on tempos the human mind struggles to inhabit. But the essential lesson is accessible. Massive change can give way to slow, accumulative processes that produce conditions for novelty. A planet that had been molten to its core, learned with great difficulty and over long epochs, to hold at its surface a set of chemical and physical constraints hospitable to persistence. The moon that was flung into orbit by fire smoothed the planet's tilt, turning chaotic orientations into a seasonal metronome. The core that formed in the wake of impact breathed a magnetic breath that preserved atmosphere against the sun's raw hunger. The crust that crystallized, even in ragged patches, provided the contact points for weathering and hydrothermal exchange. In the end, cooling is a story of becoming slow. It is an elegy for heat and an ode to patience. It is the moment when the world, transformed by violence, begins the long experiment of keeping what it had won. The planet's surface would never be quiet in the human sense. Volcanoes would continue to speak, tides would continue to pull, and impacts would still arrive. But cooling opened the possibility of endurance, the possibility that pockets of relative calm might persist long enough for deeper, stranger things to emerge. It is a reminder that in cosmic histories, as in human lives, intensity often yields to persistence, and that some of the most consequential transformations occur not with a single bright flash, but with a long sustained letting go. What does it mean for a planet to put on a skin, to slide, literally and chemically, into a new identity? It is an image at once intimate and enormous, a raw globe, still scarred and incandescent from its birth, beginning to don layers that will mediate every future interaction with its environment. In that slow dressing, the distinction between inside and outside is born. The planet acquires an interface, an atmosphere, a crust, a first set of continents, and with that interface comes the possibility of persistence. For Earth, this was the moment when heat and impact gave way to chemistry, and chemistry to habitability. The earliest breath that Earth inhaled was not the one remembered by living things. In the crowded nursery of the solar system, proto-Earth would have trapped a shroud of hydrogen and helium as it accreted, the primary atmosphere, the lightest and most ephemeral kind. Those gases were the easiest to acquire, abundant in the primordial disk they hovered within the planet's gravitational reach during the first few million years. Yet they were also the most disloyal. The young sun was energetic, its ultraviolet and extreme ultraviolet radiation more intense than it is today. Solar winds were harsher, thermal energies high. Hydrogen, light, and nimble, found ways to flee. The planet's elevated temperatures, aided by the planet's residual heat, by giant impacts that repeatedly reheated the surface, and by the lack of a strong magnetic shield at first, conspired with stellar aggression to drive the light gases away. There was a criticism, almost a cosmic editing, at work. The physics of escape, thermal escape, where atoms in the high tail of the Maxwellian velocity distribution exceed escape velocity. Hydrodynamic escape, where escaping hydrogen drags heavier species with it, acted like a sieve on atmospheric composition. The primary atmosphere, dominated by H2 and He, leaked into space as readily as steam from a boiling kettle, where the larger gas giants held their envelopes with indifferent ease. Earth's modest gravity and hostile environment meant that the first breath did not last. This loss was not merely subtraction, it was a reset. The planet could no longer rely on acquired nebular gas as a long-term envelope. If an atmosphere would endure, it would have to be forged anew. The second atmosphere, then, arrived by other means, not by capture, but by exhalation. The planet's interior began to cough and vent, a long and irregular outgassing that would define the chemistry of the air for its first enduring epoch. Magma, when it rises and decompresses, releases what it was carrying in solution: water vapor, carbon dioxide, nitrogenous species, sulfur compounds, and traces of noble gases. Those volatiles had two origins. Some were primordial, trapped in the minerals that condensed in the growing planet. Some were external, delivered later by a rain of comets and volatile-rich asteroids. Every eruption, every fissure, was a small act of atmospheric construction. This secondary atmosphere was heavier, chemically richer, and more consequential than its lost predecessor. It smelled, in the terms of molecules, of steam and sulfur. It was dense in greenhouse gases. Carbon dioxide and water vapor together established a thermal blanket that arrested the planet's rapid cooling in places, preventing a universal freeze and enabling pockets of persistence. Nitrogen, comparatively inert but volumetrically significant, accumulated to become the backbone of atmospheric pressure. Sulfur dioxide and other reactive gases shaded the sky with hazes, driving an optical character alien to modern eyes. A pale ochre-filtered sunlight, sheets of aerosol and suspended ash, a diffuse twilight even at noon. Yet even this second atmosphere was precarious. The young sun's vigor still mattered. Its particle flux and flares could strip molecules from an unprotected envelope. Here, the nascent magnetic dynamo, the product of the convecting ion within the newly formed core, played an outsized role. If the dynamo achieved coherence quickly enough, it generated a magnetic cocoon that deflected charged particles and reduced sputtering of the atmosphere into space. If not, the planet would be subject to the same erosive wind that hollowed Mars. The timing was cruelly important. A late-starting dynamo could mean the loss of volatiles just when the surface was trying to settle into a habitable configuration. Outgassing and impact delivery were in tension. Large impacts had the dual personality of donor and thief. They could deliver water and organics locked in cometary ices. They could also vaporize existing reservoirs, inject kinetic energy into the atmosphere, and impart sufficient momentum to blast gas into space. The interplay of these processes shaped the inventory of volatiles that would be available for oceans and weather. Isotopic evidence in modern rocks, ratios of deuterium to hydrogen, noble gas signatures, carry faint but instructive fingerprints of this chaotic accounting. They suggest that, though some water may have arrived late, the planet already harbored significant volatiles early on, enough that, once conditions allowed, condensation into liquid could proceed. It is in these moments of condensation that the notion of a planetary skin becomes literal. As steam condensed and rain returned, shallow pools and, eventually, broader seas could begin to exist. The appearance of liquid water on the surface was a phased transition of the highest order. A chemical solvent, a thermal regulator, a mechanical agent of erosion. Water's presence altered the pace and palette of surface chemistry. Where formerly vapors met rock, they now met an aqueous medium capable of dissolving, transporting, concentrating, and reacting. The first rains were not gentle. They arrived in a world still prone to violent heating. Scoured by acidic storms rich in volcanic gases, they carved, transported, and laid down the earliest sediments. Over time, as bombardment mellowed, pools of stability deepened. Concurrently, tectonic and magmatic processes were beginning the slow work of fashioning continents. The first crustal fragments were not continents as understood today, but buoyant rafts born from chemical and mechanical differentiation. Where partial melting of basaltic crust in the presence of water produced lighter, silica-rich melts, those melts could rise and consolidate as more felsic, buoyant material. In the convective convulsions of the mantle, these buoyant bodies tended to survive longer against recycling. They welded into proto-continents, irregular, transient, and often at the mercy of impact and volcanic resurfacing, but they were crucial. A new, heterogeneous outer shell that differed in composition and behavior from the underlying mantle. The first patches of continental crust acted like an epidermis in miniature. They provided islands of chemical stability and sheltered niches for persistent waters. Where these crustal islands intercepted rain and runoff, rudimentary weathering set to work. Minerals broke down, ions entered prebiotic soups, clays formed and acted as surfaces for adsorption and catalysis. The contrast between old molten seas and the nascent solid crust was not simply physical, it was informational. The crust began to archive events in its stratigraphy, ash layers, lava flows, and sedimentary beds that would, if preserved, become the earliest pages of Earth's geological book. But this new skin was fragile. It could be shredded by subsequent impacts, buried by flood basalts, or remelted by mantle overturns. Fragility, however, is not insignificance. The presence of a crust altered heat transfer, it tuned volatile cycles, and it created chemical interfaces where gradients could persist. Gradients, changes in temperature, redox state, or concentration, are the engines of chemistry. The early Earth, with its atmosphere of greenhouse gases, its emerging magnetic shield, its nascent continents and shallow seas, fostered a mosaic of such gradients. Hot vents where reduced gases met oxidized water. Tidal pools alternating between wet and dry under the pull of a newly born moon. Oxygen-poor waters rich in dissolved minerals. Each gradient was a small battery, offering free energy for reactions to exploit. The moon's tidal hand, an inheritance of the giant impact, mattered here as well. Tidal modulation mixed shallow waters, creating cycles of flooding and concentration that could concentrate organics and mineral solutes. Tides drove currents that redistributed heat and nutrients. They also mechanically stressed crustal margins, facilitating cracks and conduits through which hydrothermal fluids could flow. The presence of a relatively large satellite thus converted what might have been a static skin into a dynamic, flexing interface, more kinetically active and chemically diverse. There is a whisper of contingency that runs through this epoch. Had the primary atmosphere not escaped, had the dynamo failed, had impacts been slightly more or less frequent, the result could have been very different. Venus, often presented as Earth's twin, illustrates the peril of a runaway greenhouse. Thick CO2, crushing pressure, an atmosphere that has become its own coffin. Mars shows the other extreme, where loss of atmosphere and cooling led to a thin, cold world unable to sustain surface liquids for long. Earth's outcome owed something to chance as well as law. The right balance of mass, the right timing of core formation and dynamo initiation, the right mixture of impact delivery and atmospheric retention. As the planet acquired its skin, the tone of the narrative changed from violence to possibility. The atmosphere, once light and ephemeral, became a mediator between interior and space, between sunlight and rock. The crust, once molten and transient, began to persist in patches that could support repetitive processes over geological time. The first continents and the first atmosphere together created a world where chemistry might leave traces that last. They turned a planet into a place with history. Yet the nascent skin did not promise complexity, it only permitted it. The presence of water, volatiles, and chemical gradients allowed longer, more patient experiments. Molecules had time to sample combinations, polymers could form in sheltered niches, and catalytic minerals could amplify certain pathways. The environment was still harsh by any modern standard, radiation levels higher, auroras frequent, skies thick with aerosols. Acidity from volcanic emissions could be corrosive, temperature swings could be extreme. But within those margins, in the quiet persistence of pools and the warm mineral-rich breath of vents, the conditions for prebiotic chemistry were being set. In contemplating this stage, a modest human emotion surfaces in the narrator's style, a blend of wonder and humility. Wonder at the sheer improbability of a planet assembling a coherent skin amid such turbulence, humility before the fragile choreography that separated obliteration from endurance. The first atmosphere and the first continents were not guaranteed outcomes. They were emergent properties of a system governed by physics and flavored by chance. They were epochal because they enabled subsequent chapters, the long chemical experiments that, if fortune continued to be generous, could eventually give rise to the first flickers of metabolism and, much later, to creatures capable of asking about their own origins. So when the narrative turns to the first skin, the image to hold is a lined, living-like boundary, a heavy, steam-rich sky settling into chemistry, a crust that has learned to float in places, a planet that, inch by geological inch, grows a membrane between its interior and the void. It is a fragile armor, a pragmatic adaptation, and an invitation. To look at Earth at this juncture is to see a world not yet hospitable, in the way humans understand the word, but hospitable enough for long, patient processes to begin their slow work. In deep time, the adoption of a skin is less a triumph than a beginning, the first step away from raw creation and toward the curious instability of life. What would it mean, on a planet freshly hauled from fire, for rain to become not a weather event, but a geological act, an event that lasts longer than an empire, longer than languages, longer than the remembered lives of whole species yet to be born? The image is deliberate and disturbing, a sky that does not clear, a world being rained upon until landscape and chemistry themselves are rewritten. The rain that never stopped was not a single gentle downpour. It was a succession of torrential episodes, a relentless choreography of condensation and release that played out as the young Earth negotiated the new balance between vapor and cool. The atmosphere, swollen by volcanic exhalations and the vaporized remnants of impacting ices, carried a vast reservoir of water in the form of steam. That reservoir had been mobilized by two primary processes: the release of volatiles from a still restless mantle and the delivery of icy material from the outer solar system. Comets and hydrated asteroids, frozen time capsules from the cold reaches beyond the frost line, intersected the planet's path and, in doing so, contributed significant quantities of water. Some of that water flashed to vapor on contact with the hot surface. Some survived to join the thick, steam-laden sky. Condensation began where the world could get cold enough for long enough. Night after night, in high-latitude shadows, in the lee of a nascent continental outcrop, and within the deep depressions gouged by ancient impacts, steam surrendered to the radiative pull of space. Clouds condensed not into the kind of soft, whispering mists familiar to human memory, but into rolling, iron-laden anvils of liquid driven by a thick, abrasive atmosphere. Rain fell in sheets and curtains, in curtains interleaved with volcanic ash and glassy spherules, in flashes of sulphurous, acidic water that would etch and dissolve rock as readily as sculpted sand. The chemistry of that precipitation was decisive. The air had not yet been touched by photosynthesis. There was no free molecular oxygen to buffer reactions. Instead, it was heavy with carbon dioxide, sulfur dioxide, hydrogen sulfide, and other volcanic byproducts. When CO2 dissolved into falling water, it became carbonic acid. When sulfur gases met water, they formed stronger acids. The result was rain that tasted, in chemical terms, of dissolution. It was corrosive, aggressive, and efficient at transferring the volatile inventory of the atmosphere into the lithosphere. Where this rain persisted, it stripped cations from silicate minerals and carried them into the running waters that formed. Basalt, the ubiquitous rock type of a young crust, bled ions into these rivers. Feldspars and other minerals, surrendered elements that would soon be the raw material for new sediments and for the ocean's changing character. The physical drama was no less potent. Consider a single, prolonged storm that might have lasted months, decades, or, in the scale of deep time, millennia as part of a larger epochal pattern. Thunderheads would tower to heights not familiar today, driven by the energy locked in a dense, steam-rich column topped with aerosols that trapped heat. Lightning, plentiful and violent in such convective regimes, would crack the sky with regularity, its electrical discharge a probe into chemical potential. Every strike was a transient furnace that dissociated molecules and created radicals, brief sparks of reactivity that, in later epochs, some have speculated, could play roles in prebiotic chemistry. For now, they were part of a chemistry of shock and change, not of biology. Rivers emerged as the rain ran off and pooled. At first, many of these channels were ephemeral, flash flood gulches that scoured the new crust and then vanished beneath ash or lava. But where crust had endured, where basins were protected, water accumulated into more permanent conduits. These rivers were not placid. They were energized by steep gradients, fed by intense input, and loaded with sediments. Erosion worked at rates inconceivable in modern temperate settings. Basaltic uplands retreated, valleys incised, and sediments were swept toward low-lying basins and coastal margins. In those depositional sinks, layers began to stack. Ash beds interleaved with clastic sediments, chemical precipitates, and the first thin veneers that could survive deep time to become the earliest sedimentary records. The oceans that these rains helped to form were not the serene blue expanses imagined in later geological chapters. They were dark and metallic, rich in reduced iron, dissolved sulfides, and a cocktail of elements liberated from a freshly weathered crust. In an anoxic environment, iron stays soluble as Fe2+ and accumulates in seawater. The young seas, fed by aggressive runoff and by hydrothermal inputs along volcanic ridges, took on a palette of deep russet and ochre in a geological imagination, a world of dissolved metals waiting for the right trigger to be locked into rock. This trigger did not require oxygen. Chemical gradients, local oxidants introduced by atmospheric processes or by mineral interfaces, could precipitate iron even in the absence of global oxygenation. But the overall picture remained: oceans that were laboratories of reduced chemistry, with vast capacities to store carbon and metals. The solubility of carbon dioxide in the sea ensured a dynamic between the atmosphere and the ocean. CO2 dissolved into water, forming carbonic acid, which could weather rocks more effectively and, over time, lead to the precipitation of carbonate minerals in cooler, sheltered locales. Yet the high acidity and high levels of dissolved CO2 meant that widespread, stable carbonate platforms, the limestone seas familiar from later eons, were a delayed phenomenon. The balance between dissolved carbonate chemistry and the ongoing volcanic flux proved precarious. Tides, energized by a moon born from a violent collision, lent a rhythmic violence to these waters. Where tidal forces bent shallow crustal margins, they stirred sediments and mixed chemical layers. Tidal pumping of water into porous coastal rocks produced repeated wet-dry cycles in marginal pools, concentrating solutes and creating niches where physical and chemical repetition could do the slow work of sorting molecules. These cycles were important, not because they favored life at that stage — there was no life, and no oxygen to sustain it — but because they created the persistent, repeatable patterns that allow complexity to accumulate. Repetition is a necessary precondition for any system to move from chance to pattern. The tides provided that repetition on the young Earth. The relentless rains also acted as an atmospheric thermostat of an unusual kind. Evaporation and condensation transport latent heat, and this cycling helped to redistribute energy across the young globe. Yet the effect was double-edged. On the one hand, persistent vapor and cloudiness increased the greenhouse effect, trapping heat and slowing the complete solidification of the planet's upper layers. On the other hand, condensation and precipitation returned heat to the surface and enabled the transfer of energy back to space in pulses. The net result depended on the balance of greenhouse gases and aerosols. Volcanic aerosols, particularly sulfuric compounds, tended to reflect sunlight and could induce local or global cooling episodes. The climate system of this period was therefore wildly variable on human scales, but when averaged over millennia, it tended toward a slow moderation. Heat would leak to space. Ocean basins would deepen, the atmosphere would carry less free steam as more water became sequestered in liquid reservoirs. One of the geological consequences of prolonged rain was the acceleration of weathering-driven carbon sequestration. Rainwater, enriched in dissolved CO2, reacts with silicate rocks in a fundamental chemical dance. Cations liberated from mineral structures combine with dissolved carbonate species and are transported to the sea, where they can precipitate as carbonate minerals. Over long timescales, this is one of the planet's main mechanisms for removing CO2 from the atmosphere and storing it in rock. On a young Earth, the intense rates of weathering, driven by aggressive, acidic rain, may have been one of the few effective brakes on an otherwise runaway greenhouse. But the process required time. For every ton of gas sequestered, the crust and the ocean's chemical bookkeeping had to make room. The rain that never stopped wrote vast entries in that ledger. Hydrothermal systems, fed both by meteoric water percolating downward and by seawater circulating near volcanic heat sources, created localized chemical furnaces where gradients were greatest. Water that sank into the crust, encountered heat and reactive rock, and then returned to the surface carried with it reduced gases, dissolved metals, and complex mineral assemblages. Hydrothermal plumes discharged into early seas, creating chemical boundaries and mineral precipitates. These plumes were abundant, their global distribution tied to the vigorous volcanism of the time. They established pockets of intense chemical potential that, later in Earth's narrative, would serve as fertile ground for more complex chemistry. Yet none of these processes implied biology. The narrator must be explicit. There was no oxygen and no life. In the atmosphere of that epoch, oxidants were rare and localized, and while they could drive particular mineral precipitations, they were not global agents. The absence of O2 shaped the chemistry of lakes and seas, kept many elements dissolved, and meant that the early planet's energy landscapes were governed by redox couples very different from those familiar in modern surface ecosystems. It is tempting in hindsight to see these conditions as preparatory steps toward life. It is also necessary to be patient. The chemistry of oceans and atmospheres needed to stabilize around a complex interplay of sources and sinks before biological systems could even get a foothold. The persistence of heavy rain for epochs had other, more prosaic consequences as well. Sedimentary basins began to build thicknesses of material that would, after burial and lithification, become the first stratigraphic records of Earth's infancy. Layers of ash from distant eruptions interleaved with chemical precipitates and detrital clastics gave future geologists, billions of years hence, a palimpsest to read. Those early archives are sparse and fragmentary. Much has been recycled by tectonics and later impacts, yet they preserve crucial clues: mineral textures, isotope ratios, and sedimentary structures that betray conditions of formation. When modern scientists read these signatures, the tale of interminable storms emerges not as anecdote but as inference. Patterns of erosion, deposits suggesting rapid runoff, and chemical fingerprints of high atmospheric CO2 and low oxygen. There is a subtle, almost human irony to this epochary rain. Water is the universal solvent of life, yet in its earliest global abundance, it scoured the planet in ways hostile to nascent organic complexity. Acidic storms dissolved nascent mineral lattices and delivered ions that made the seas chemically crowded. Lightning and hydrothermal discharge generated reactive species and energetic intermediates. Tides and currents mixed and homogenized. The conditions were dynamic, energetic, and full of potential, but they were not yet the calm, buffered seas that would later cradle biomolecules. The steps from potential to realization are not instantaneous. They require not only ingredients, but the attenuation of hostility and the emergence of stable, localized niches. Over millennia, the planet shifted. Rainfall epochs waxed and waned with the balance of outgassing, the decline of impact rates, and the evolving character of solar output. More water accumulated in the oceans, the atmosphere gradually lost some of its extreme volatility, and weathering slowly drew down greenhouse gases. The cumulative effect of episodic downpours was to transform a planet whose surface had once been dominated by incandescent rock, vapor, and ash into one where liquid water was a persistent agent of change. Rivers carved networks, basins filled, continental margins formed, and the first durable sedimentary shelves began to appear. The story of the rain that never stopped is, ultimately, a story about time and intervention. It is an account of how a single, volatile, water, can rewrite planetary destinies when its phase is liberated across an entire world. It shows how the interplay of geology and atmosphere can create feedback loops. Rainfall accelerates weathering, which modifies atmospheric composition, which alters climate, which changes precipitation patterns. These feedbacks are neither teleological nor moral. They are processes governed by physics and chemistry, by chance and necessity. Yet their operation produces arcs of change so profound that the Earth that emerged after epochs of relentless rain was unrecognizable compared to the molten body that had once dominated the solar nebula's margins. For the human listener trying to map meaning onto this ancient drama, the rain that never stopped instills a particular humility. It recalls how persistent, small-order processes, drops of water falling unceasingly over generations, can sculpt continents, sequester vast quantities of carbon, and reset the chemical theatre upon which future innovations will act. There is no romance in the image of interminable storms. There is, instead, a kind of austere reverence. What seems merely climatic in a human lifetime is, in geological time, an edit to planetary identity. The rains did not create life in a single storm, nor did they supply oxygen in a single downpour. They did something perhaps more consequential. They made the planet capable of keeping what it had been given, of converting fugitive vapor into lasting seas, and of establishing the conditions under which, in much longer futures, chemistry could take the next step. So when the narrator surveys this epoch, the image to hold is both grand and intimate. Oceans forming drop by drop, rivers beginning to write the contours of continents, acid rains etching the bones of the crust, and hydrothermal chimneys breathing chemical plumes into anoxic seas. There was no oxygen and no life, but there was motion, material exchange, and a slow, patient inscription of memory into rock. The rain that never stopped was, paradoxically, what allowed the planet to stop being merely a molten furnace and to start being a world with history. What does a world do when it finally learns how to hold water? The question is not rhetorical so much as tectonic. A planet that has spent its infancy as incandescent rock, vapor, and ash must pass through a kind of graduation, a slow acquisition of patience. The first oceans were not a postcard moment, a single planet-wide puddle appearing between chapters, but a drawn-out settling, a long act of negotiation between atmosphere, crust, and space. In those deep basins, something new became possible. Temperature regimes that hardly changed over centuries, chemical gradients that could persist for millennia, and sheltered places where complexity could be tried again and again without instant annihilation. The filling of the basins was a story of friction and timing. Steam condensed in pockets, in the shadows of highlands, in the lee of early crustal rafts, in the deep hollows gouged by impacts, and wherever cooling found purchased droplets pooled and did not immediately evaporate. Outgassing from the mantle continued to feed the sky. Icy visitors from the outer system punctuated the flux. Each cometary kiss, each volcanic exhale tipped a planetary-scale balance. Over millions of years, the trickle became a sheet, the sheet deepened into seas, and seas merged into oceanic basins that would come to cover most of the young world. The surface that had once been a searing skin of magma now wore an immense, vestless membrane of water. Depth matters more in deep time than it does in a human lifetime. The first oceans were deep in multiple senses. They were geographically deep, plunging into trenches and basins that exceeded the reach of sunlight and surface weather, and they were temporally deep. Water stores heat and chemical inventory and, crucially, buffers change. Unlike air, water has a high heat capacity and mixes by convection and currents. 100 meters of ocean can smooth daily temperature swings, and kilometers of depth can mute seasonal and even tectonic volatility. Where a shallow pool can flash to steaming vapor under a fresh impact or eruption, a deep ocean can absorb that energy, redistribute it, and remain liquid. In a planet still subject to errant meteors, volcanic surges, and fierce winds, the ocean offered the first real refuge of continuity. That continuity was not homogeneous. The ocean carved itself into regimes. Near the surface, sunlight, though attenuated by volcanic haze and high atmospheric opacity, still warmed upper layers and drove winds and waves. The surface layer remained turbulent, exchanging gases with the atmosphere and hosting storms that could be brutal. Beneath that, the thermocline separated sunlit agitation from a deep, colder stability. There, in perpetual darkness, temperatures trended slowly toward those of the abyssal mantle. Without oxygen to complicate matters, the chemistry of that dark water was dominated by reduced iron, dissolved sulfur species, methane, and dissolved carbon dioxide in abundance. In a modern mind, these might read as inhospitable ingredients. In the chemistry of origins, they were raw materials, energetic asymmetries, and potential bonds waiting for the right scaffold. Nowhere did the ocean's buffering role show itself more dramatically than at its intersections with fire. Hydrothermal vents, the chimneys and fissures where the planet's internal heat met seawater, became localized theaters of chemical complexity. In the convulsive infancy of Earth, submarine volcanism and vigorous circulation of seawater through newly formed crust produced two contrasting vent environments. Black smokers exhaled superheated, mineral-rich plumes of iron and sulfide into cold, anoxic water, alkaline vents, born of serpentinization reactions where mantle rocks interact with water, spewed comparatively cooler, hydrogen-rich fluids. Both created steep redox and pH gradients. Both created porous mineral structures that acted like 1,000 tiny chemistry labs, channels, cavities, and microenvironments in which dissolved molecules concentrated, reacted, and were repeatedly cycled. The physical form of these vents mattered. Chimneys of sulfide minerals accreted like chimera columns. Their porous walls trapped fluids and created microcompartments. In course after course of flow, gradients established across membranes of mineral, hot reduced fluid on one side, colder, more oxidized seawater on the other. Those gradients performed the essential work of thermodynamics. They offered free energy that could be tapped to drive endergonic reactions, the very sorts of reactions necessary if simple molecules were to assemble into longer chains, folded structures, or metabolic networks. The vents, then, were not merely chemical curiosities, they were engines that sustained disequilibrium. In a universe where the steady beat of entropy tends to smear contrasts into sameness, vents preserved the abrupt contrast that chemistry needs to climb toward complexity. Hydrothermal realms had additional virtues. Minerals precipitated there, iron sulfides, nickel-bearing phases, and clays provided catalytic surfaces. Iron-sulfur minerals in particular bind and activate small molecules and have been invoked repeatedly as plausible facilitators for the construction of more complex organic compounds. Clays, which form from the weathering of silicate rocks, absorb and concentrate molecules on their layered surfaces, providing geometric constraints that favor polymerization. In the porous walls and sedimentary drapes around vents, molecules could be confined, reoriented, and re-exposed to cycles of heating and cooling or wetting and drying. The same compartmentalization that is essential for cell-like behavior could be produced by mineral architecture long before any lipid membranes were around to do the job. Yet vent systems were only part of the ocean's chemical repertoire. The open seawater itself was a repository of dissolved metals and gases. Basaltic weathering released cations, calcium, magnesium, and iron into streams and coastal runoff. Acid-rich rains discussed in the earlier epoch accelerated that leaching. In the absence of oxygen, iron remained mostly soluble as Fe2+, coloring the young seas with dissolved metal and maintaining a stock of redox active elements. Where local oxidants, produced by photochemistry in the upper atmosphere or by mineral-driven processes, encountered iron-rich water, precipitation of iron minerals could occur, creating layers of sediment that would, much later, become the distinctive banded iron formations recorded in the geological archive. Those formations, however, were the consequences of long-term interplay between atmosphere, ocean, and whatever nascent oxidizing processes might eventually appear. In the first oceans, these were possibilities, not yet realities. Salinity and ionic balance deserve attention because they determine the behavior of many chemical systems, as rivers and hydrothermal flux delivered salts to the sea, ionic strength rose, influencing the solubility of organics and the stability of polymers. High ionic concentrations can both stabilize and destabilize macromolecular structures. Certain ionic milieus favor the folding of RNA-like strands, while others promote aggregation or precipitation. The ocean thus functioned as an experimental matrix with variable parameters, pH, salinity, temperature, metal concentration, and redox potential, all varied across space and time. Different locations, shallow, tidal flats, deep-sea vents, continental margins, offered different permutations of these variables, which meant that anywhere the first chemistry had a chance to progress, it could do so under many different conditions. Tides, once again, played a subtle but crucial role. The moon's influence, born of prior catastrophe, turned into a methodical kneading of shallow waters. Tidal cycles drove wet-dry rhythms along coasts and shelf regions, concentrating solutes and subjecting molecules to dehydration. Rehydration cycles that promote condensation reactions, bonds forming as water is expelled. Tidal pumping flushed shallow, porous rocks with seawater, delivering reactants to subsurface niches and then drawing them out again. Rhythmic forces also mixed surface waters, helping to distribute chemical species and to fracture thermal layers that would otherwise be stably stratified. In short, the moon converted an otherwise static ocean into a dynamic laboratory with temporal structure, repetition that, in chemistry as in life, is a prerequisite for accumulation. Stability in the deep sea was, paradoxically, both enabling and limiting. Deep waters were thermally stable and shielded from the UV assault that a thin, early atmosphere could not fully mitigate. That shield allowed molecules that might be destroyed at the surface to persist and interact for longer durations. On the other hand, the darkness and high pressure of the abyss limited processes that require light-driven chemistry. The ocean's verticality therefore created a division of labor. The surface and near-surface zones would be the playground of photochemistry, aerosols, and atmosphere. Ocean exchange, the deep zones, would be the workshop for redox chemistry driven by geothermal energy. Where these regimes intersected, at coastal margins, in hydrothermal plumes that rose into colder water, and in the fine-grained sediment layer at the seabed, the richest chemical conversations occurred. The ocean also became the planet's first long-term archivist. Sediments slowly accumulated, trapping chemical and mineral evidence of atmospheric composition, volcanic eruptions, and the ebb and flow of hydrothermal activity. Chemical fingerprints, isotope ratios, trace element distributions, mineral textures were stored in layers that would survive, in rare places, the churn of plate, tectonics, and impact gardening. These archives would, billions of years later, allow distant descendants to read the story of Earth's infancy. But at the time the sediments were forming, they did something else. They removed material from rapid cycling and stored it. Sedimentation sequestered carbon, iron, sulfur, and other elements into slow geological reservoirs, altering the chemistry of seawater and atmosphere in ways that would feed back on climate and reactivity. What the first oceans did not do was make life inevitable. They created opportunities, not guarantees. In the dark pools and at the foot of vents, the raw ingredients and energy gradients existed, and these were necessary preconditions for self-organizing chemistry. But chemistry needs both ingredients and time, the right surfaces, the right cycles, and, critically, the repeated exposure to fluctuations that allow systems to test variance and retain what works. The ocean supplied many of these conditions simultaneously. Steadiness in depth paired with periodic agitation, abundance of reduced compounds paired with oxidants delivered sporadically by photochemistry, mineral catalysts juxtaposed with fluid dynamics that refreshed reactants. In that sense, the ocean was an environment optimized by accident for experimentation. The emotional contour of this scene is not one of triumph but of fragile hope. Imagine a world that has been relentlessly remade by impacts and fire, finally offering up regions where chemistry can persist beyond an instantaneous insult. The oceans were not passive receptacles. They were active partners in a planetary experiment. They absorbed the planet's fury and smoothed it. They carried and concentrated elements, they formed gradients and compartments, and they recorded the history of those processes in their emplaced sediments. If some future sequence were to lead to self-sustaining chemistry capable of evolution, it would most plausibly arise in the interstices the oceans provided. There are contradictions to hold in mind. The same oceans that buffered extremes also homogenized and diluted. The same tidal mixing that created repetition could wash away nascent concentrations. Mineral catalysts bind and promote reactions, but also destroy delicate structures. Deep time teaches patience with these tensions, persistence, repetition, and a plurality of environmental niches increase the odds that one setting will, by slow accumulation, find a path forward. In the end, the first oceans did something simple and profound. They made time behave differently. Heat and impacts operate in abrupt pulses. Water grants a slowness, a capacity for processes to run their course without being instantly erased. That slowness is the medium in which complexity can take root. The planet's long story of matter rearrangement, from dust to rock to metal to vapor to liquid, reached a turning point when the oceans stabilized enough to let chemistry play out at the timescales it needed. In those deep, dark, chemically vibrant bodies of water, under the hush of an anoxic sky and the ceaseless tug of a new moon, the first patient experiments of chemistry were sheltered. They were small and fragile, but they were no longer singular. They could be repeated, iterated, and, in time, amplified. The ocean was not yet life's cradle, only its most plausible workshop. But it was, without question, the first place on the planet where the slow alchemy of deep time and wet chemistry could finally begin to whisper possibilities aloud. What does it look like when the first letters of a language are scrawled into a world that has never written before? It is a question that compresses the drama of chemistry into a single, stubborn image. A flash of light, a hiss of steam, a darkening pool where molecules meet and fail, and sometimes, by pure accident, succeed. In the long silence after magma and meteors, Earth kept whispering experiments into its wet places. Those whispers were electrical and thermal, corrosive and catalytic. They were the raw gestures by which simple atoms began to assemble into the first organic syllables, amino acids, the building blocks that, much later, would compose sentences of metabolism and the grammar of heredity. On an early planet still shedding heat, storms were not polite affairs. The dense, volatile, rich atmosphere that had been woven by volcanoes and impacts convected like a living machine. Lightning was endless and furious. Electrical filaments arcing through a sky heavy with steam, carbon dioxide, nitrogen and sulfur-rich fumes. Where a lightning bolt struck the upper layers of the atmosphere or crashed into a surface pool, it was not merely light that flashed. Chemistry was jolted out of equilibrium. Molecules that normally preferred to sit inertly in gas phase. Molecular nitrogen, carbon dioxide, methane where present, ammonia in pockets, were torn apart into radicals, ions and fragments. Once free, these fragments recombined in new arrangements. Simple pieces, hydrogen, carbon, nitrogen, oxygen, found each other in bewildering combinations. Under the energetic blow of electric discharge, the first amino acids could be synthesized. Glycine, alanine, as if the sky itself were experimenting with the alphabet of proteins. The idea of electricity forging organic molecules is not invention. It is an insight born from both laboratory and observation. In the 1950s, a simple experiment, an artificial thunderstorm in a flask, produced a suite of amino acids from a primordial gas mix. The experiment was emblematic. Energy poured into a reducing mixture of gases can yield organic complexity. But Earth was not a single, idealized flask. Its gases were not uniform. Modern understanding complicates the neatness of that early demonstration. Much of Earth's atmosphere soon after formation may have been dominated by carbon dioxide and nitrogen, not the strongly reducing gases used in the classic lab setup. Yet the planet did not need a globally reducing air to make organics. It only needed pockets, local theatres where chemistry bent in unusual ways. Volcanoes provided many such theatres. Plumes rising from fissures were chemical cauldrons where reducing species could concentrate. The inner plumbing of the planet, rich in hydrogen and carbon compounds, exhaled gases into the shallow atmosphere and into seawater. In the acidic smokestacks above fumaroles, high-temperature chemistry forged precursors: hydrogen cyanide, HCN, and formaldehyde, HCO, molecules that are obscure in daily life but foundational in organic assembly. HCN is a small, nitrogen-rich compound capable of participating in pathways, Strecker-type syntheses that assemble amino acids when combined with aldehydes and ammonia. Formaldehyde is a molecular carpenter, a building block for sugars through the Formose reaction. Both could be produced in abundance around volcanic vents, in impact-heated plumes, and in the irradiated layers of the atmosphere. There was also a cosmic delivery service. Meteoritic material and comets, battered remnants of the solar system's colder reaches, arrived carrying organics already formed in space. The Murchison meteorite, a 20th century messenger, shocked the modern world by bearing a diverse inventory of amino acids and related organic molecules, molecules synthesized in interstellar ices and preserved for billions of years. Such extrasolar or at least extrasystemic inputs did not guarantee life, but they increased the prebiotic inventory. They reduced the combinatorial burden for Earth. Some letters of the chemical alphabet were already provided. At the margins where seawater met heat, at hydrothermal vents and in shallow, tidally influenced pools, conditions were particularly favorable for deeper steps. Vents were paradoxes of stability and violence. In the dark, high-pressure reaches of the ocean floor, seawater percolating into the crust met hot rock and returned charged with hydrogen, reduced sulfur, and trace metals. As disequilibria dissolved, hot reduced fluids meeting cold oxidized seawater chemical gradients formed that could do the work of charge separation, much like a battery. Those gradients were crucial. They provided a directional push for chemistry, a way to do the otherwise improbable work of building complexity. Mineral structures at these vents, iron sulfides, clays, and other precipitates, formed porous matrices, a labyrinth of microcompartments where reactants could concentrate and be repeatedly cycled. There, on the rough walls of chimneys, catalysis occurred. Iron and nickel sulfides combined small organic fragments, activating them toward polymerization or rearrangement. Hydrothermal systems furnished heat, catalysis, and continuous flux, three ingredients that move chemistry forward. Yet surface environments were equally plausible and, in some accounts, even more potent. The presence of a moon, born of a cataclysm that had remade the planet's angular momentum, introduced steadfast tides, persistent wet-dry cycles along coasts and shallow basins. These cycles, driven by lunar pull, were not mere seaside theatrics. They were repeated concentration mechanisms. A tide would draw seawater into a porous shoreline, leave it to evaporate under a sun or to be heated by volcanic glass, and then flood it anew. Each cycle concentrated solutes, organic precursors, salts, metal ions, imposing dehydration, rehydration regimes that favor condensation reactions, bonds forming between amino acids to give short peptides, nucleotides beginning to link, simple fatty acids aligning into primitive membranes. Where the ocean provided continuity and buffering, tidal pools provided repetition and concentration. Together, they were complementary laboratories, one deep and buffered, the other rhythmic and concentrated. The chemistry that produced amino acids was varied and opportunistic. In some locales, Strecker synthesis, starting from aldehydes, cyanide, and ammonia in the presence of water, could yield alpha amino acids, the backbone of proteins. In others, the Fischer-Tropsch-type pathways, occurring on the surfaces of metal catalysts such as iron and nickel, converted simple gases like CO and H2 into longer hydrocarbons and eventually into carboxylic acids, the precursors of lipid molecules. Formaldehyde chemistry could produce sugars, reactions involving cyano compounds and phosphorus under the right conditions could yield nucleotide precursors. The planet did not need to favor a single pathway, rather, many pathways could run in parallel across the heterogeneous mosaic of environments. Lightning-dashed atmosphere, volcanic smoke, hydrothermal chimneys, and drying tidal flats. If there was a single, universal miracle in this story, it was concentration. Chemical reactions that assemble complexity require encounters, persisting contacts between molecules long enough for bonds to form. In dilute seas or ephemeral plumes, encounters are too infrequent. Mineral surfaces, clay sheets, iron sulfide grains, porous chimney walls acted like counters in a cosmic marketplace. They bound, aligned, and occasionally catalyzed. Clay minerals, with their layered structures, can absorb organic molecules and orient them in ways that promote polymerization. Metal sulfide surfaces can stabilize high-energy intermediates necessary for bond formation. These mineral actors were not passive. They modulated the kinetics and thermodynamics of nascent organic chemistry. Another problem lurked in the background, the origin of homochirality. Amino acids, like many organic molecules, can exist in mirror image forms, left and right-handed versions. Life on Earth uses almost exclusively left-handed amino acids. How this preference arose is an open question. A handful of hypotheses converge on plausible mechanisms: asymmetric photolysis by circularly polarized ultraviolet light in certain regions of space, chiral templating on mineral surfaces that preferentially absorb one-handedness, or stochastic amplification, where tiny initial imbalances are magnified by autocatalytic chemistry. The important point for the early Earth is not that homochirality needed to be instantaneous, but that the environment offered many opportunities for symmetry to be broken and for selection to amplify one variant over another. Phosphate, an essential element in modern nucleotide backbones, posed another challenge. Phosphate is sparingly soluble and tends to lock into minerals. The question of where available phosphate came from has driven numerous hypotheses. Local concentration in evaporative basins, transient liberation from volcanic apatite under acidic conditions, activation through reaction with mineral surfaces or with condensing organics in formamide-rich contexts. Formamide, a solvent alternative discussed in some prebiotic scenarios, can both solvate and promote phosphorylation reactions under heat. Meteoritic delivery again offered a partial solution. Extraterrestrial sediments sometimes contain reduced phosphorus species that are more labile. The planet's strategy was redundancy, multiple, sometimes messy pathways that could, together, provide the necessary inventory of reactive phosphate. The inventory of organics that the young Earth assembled was not merely a collection of monomers. It included amphiphilic molecules, molecules with both water-loving and water-repelling parts, produced by fissure, Troch pathways, and by soluble precursors in hydrothermal alteration. These amphiphiles can spontaneously assemble into micelles and vesicles, the simplest approximations of cell membranes. In shallow pools subject to wetting and drying, fatty acids can form bilayered structures that encapsulate small amounts of solution. When organics became enclosed within such lipid containers, they attained a new property, a bounded microenvironment in which concentration, composition, and reaction pathways could diverge from the outside world. Protocells, rudimentary as they would have been, provided a scaffold for further chemical evolution, compartmentalization, selection, and, potentially, the managed exchange of matter. Crucially, none of this unfolded as a linear recipe. The young Earth was a patchwork. Different locales produced different inventories under varying conditions. Lightning might deliver amino acids to surface waters. Hydrothermal vents might craft nucleotide precursors and reduced organics. Meteorites might seed additional complex molecules. Transport rivers, tides, currents mixed these inventories, creating new combinations and novel encounters. In such a world, the origin of life becomes less a single event and more a tapestry of experiments, each local success or failure contributing mutations to a global chemical ecosystem. From the vantage of a deep-time narrator, there is profound contingency in this chapter. The synthesis of amino acids and other organics was not inevitable. It was probabilistic, dependent on the confluence of energy sources, available chemistries, mineral catalysts, and the novel tempering of the planet's surface by oceans, tides, and a nascent magnetic shield. The magnetic cocoon that had come into being through the convection of molten iron did more than protect. By slowing atmospheric stripping, it bought time for volatile inventories to stabilize, allowing repeated chemical experiments instead of a single sterilizing blow. There is also a moral of patience. Chemistry requires not just ingredients, but duration and repetition. Lightning is instantaneous. Hydrothermal cycling is persistent. Tides are rhythmic. Impacts are episodic. The planet's multiplicity of tempos, flashes of energy, and long, slow convective breaths created an ensemble of opportunities. In some sheltered grotto, at the mouth of a vent, or on a sun-baked tidal flat, molecules that were once wayward began to stick together long enough to form chains, rings, and networks. Amino acids accumulated, short peptides formed, lipid sacs blinked into being and held within them dense reactive soups. They did not yet know what they had become. They were at best a lexicon without grammar. Yet even that lexicon was a radical transformation, from inorganic atoms to organic monomers. Earth had begun to compose the first sounds that might later be strung into sentences of metabolism. If the thunderous furnace of formation had been the planet's dramatic opening chapter, then the slow, iterative chemistry of oceans, vents, and shores was its tentative middle act. The birth of amino acids was not a single, decisive victory. It was a series of small triumphs in an arena of hazards. Each electric flash, each volcanic exhale, each meteor's fall was a wager. Some wagers paid off. The first organic molecules did not declare victory over chaos. They merely demonstrated that, under the right orchestrations of energy and matter, order could emerge long enough to be interesting. In that sense, the birth of life's building blocks is the story of a planet learning to write. It learned first letters and syllables, the amino acids, and placed them carefully, sometimes chaotically, into pools and membranes. For a world that had spent its infancy molten and incandescent, the appearance of simple organic molecules was a soft, astonishing pivot. It was not life yet, it was the alphabet. From lightning and fire and ocean chemistry, a lexicon formed. The rest, insofar as it was permitted by chance and time, would be patience, iteration, and the improbable expansion of a vocabulary into syntax. What is the smallest voice that can change an entire world? It was not thunder or tectonic upheaval that first altered the character of Earth in a way that could be called biological. It was an exhalation of chemistry so modest that, in the human scale of drama, it seemed almost a whisper. Molecules, organized and repeating, learning to harness flows of energy and to keep time with the planet's rhythms. Around 3-8 billion years ago, in pockets where conditions permitted, those whispers assembled into persistent patterns. The planet crossed an invisible threshold. Organic chemistry began to do more than flicker. It began to reproduce, to compete, and to build architectures that would carry history forward. The scenes are small and numerous. Down on the dark, effervescent floors of young oceans, where basaltic crust bled heat and mineral-rich fluids, hydrothermal vents functioned like chemical factories. Here, seawater that had seeped into hot rock leached electrons from iron and sulfur, and when it rose again, it met cold, oxidized seawater. The encounter created gradients: hot versus cold, reduced versus oxidized, acidic versus alkaline. And across these gradients, chemistry found a rhythm. Minerals precipitated into porous chimneys and filamentous lattices. In the interstices of those mineral forms, organic molecules could concentrate, collide, and be re-exposed to fresh reactants. Energy flowed along these interfaces like a current through a coil. Not energy for light and warmth, but energy in the form of redox differences and proton gradients. In such places, proto-metabolisms could scaffold themselves. Those metabolisms took many shapes. In pitch darkness, far from direct sunlight, simple organisms learned to make a living off the Earth's own chemical supply. Chemosynthesis became a viable strategy. Hydrogen, hydrogen sulfide, ferrous iron, and methane were not pollutants but fuels. Microbes that oxidized these reduced compounds, stripping electrons from hydrogen sulfide to feed their own biochemical work, emerged as some of the earliest specialists. Their method was crude and elegant: use an available energy differential to build organic matter from carbon dioxide. Where sunlight could not reach, chemistry itself provided the engine. Nearer the shallows, where faint sunlight filtered through a hazy atmosphere, another strategy began to appear. The sun that bathed the early planet was dimmer than today's star, and its light was filtered by steam, haze, and volcanic dust, yet it still delivered photons. Primitive pigments, molecules capable of absorbing a sliver of that light, offered another route to harvest energy. The earliest phototrophs were not the oxygen-producing cyanobacteria known from later epochs. They were simpler, anoxygenic bacteria that used light to drive reactions but relied on electron donors such as hydrogen sulfide or ferrous iron, not water. Their existence painted coastal pools and shallow mats with biochemical gradients, creating surface ecosystems that beat to the pulsed rhythm of tides and storms. The first microbial communities were not solitary pioneers, but collective projects. Under the omniscient eye of chemistry, cells bound themselves together in films and matrices, secreting sticky polymers that trapped sediments and dissolved particles. These mats, thin at first and then thicker over generations, built layered structures known in later rocks as stromatolites. The layered laminae with a fossilized memory of microbial labor, successive generations trapping, binding, and cementing grains of sand and mineral precipitate. A stromatolite was an archive written in calcium carbonate and silicate, a slow-grown palimpsest that preserved the iterative choreography of growth, sedimentation, and mineralization. Life's engineering at this scale was humble but relentless. Microbial mats altered the chemistry of their immediate environment as surely as a reef alters local currents. They concentrated nutrients, established microoxic and anoxic microzones, and created sticky surfaces where organic molecules could be retained and transformed. These communities were ecological mosaics, anoxic zones beneath aerobic skins, gradients of light and sulfide, pockets of warmth where mineral exhalations met cold water. In each microhabitat, different metabolic strategies could coexist and compete. Diversity, in the early sense, meant many ways of making a living from the same set of limited resources. Metabolic innovation followed opportunities. Methanogens, microorganisms that combine hydrogen and carbon dioxide to produce methane, were subtle chemical artisans of the deep. By releasing methane to the ocean and atmosphere, they contributed to greenhouse forcing in a world of faint sunlight. Methane is an extraordinarily potent greenhouse gas on short timescales. Elsewhere, iron-reducing and oxidizing microbes shuffled iron between dissolved and mineral forms, precipitating iron-bearing sediments that would become important markers in the geological record. These tiny actors did not know they were architects of planetary change. They simply exploited available reactions and, by doing so persistently across millennia, rewired surface and near-surface chemistry. A central puzzle of early life was energy management, how to capture and use energy reliably in an environment of abrupt perturbations. One emerging solution was to exploit pre-existing proton gradients. Alkaline hydrothermal vents in particular offered a tantalizing mechanism. Fluids rich in hydrogen and with high pH flowed out into relatively acidic seawater, setting up natural proton differences across thin mineral barriers. These proton gradients, akin to the gradients used by modern cells, can drive the synthesis of energy packets such as ATP. In that sense, life may have learned to plug into geochemical batteries before evolving complex internal machinery to recreate them. The implication is crucial. Life's earliest energetics were not engineered wholly within cells, but borrowed from the planet's inherent disequilibria. Structural simplicity paired with chemical cunning. The earliest cells were likely small and streamlined, enclosed by lipid membranes that formed spontaneously when amphiphilic molecules concentrated in evaporating tidal pools or around vents. Those membranes provided a boundary, a primitive cytoplasm, where selective chemistry could proceed with less interference. Within these bounded volumes, polymers could emerge and be tested. Some sequences of nucleic acids or peptides persisted better than others, and the environment, tidal cycles, wet-dry rhythms, and thermal gradients favored repetition. Compartmentalization was not merely physical, it was the first step toward inheritance, a way to keep a favorable mix of molecules together long enough for their collective behavior to be passed on. Fossil and isotopic evidence, sparse but resonant, bear witness to these moments. Carbon isotope ratios in ancient sediments suggest that biological carbon fixation, the process of transforming inorganic carbon into organic molecules, was already fractionating carbon roughly along the lines observed in living organisms. Microfossils and laminated structures in rocks dated to near this era hint at diverse microbial architectures. These clues do not reveal lineage trees or species lists. They reveal process, reproducible chemical and structural outcomes produced by life's persistence. The emergence of microbial life introduced feedbacks that connect the microscale to planetary dynamics. By fixing carbon, microbes drew down atmospheric CO2 and stored it in biomass and sediments. By respiring and fermenting, they returned gases like methane and CO2. By oxidizing or reducing metals, they changed ocean chemistry and sediment composition. Over geological spans, these fluxes accumulated. Banded iron formations, deposited widely in later eras, testify to large-scale interactions between iron-rich seawater and the oxidative capacities of biological or chemical processes. The earliest microbes set in motion cycles whose integrated effects would become visible to geologists billions of years later. Yet origin narratives must guard against teleology. The microbes were not building toward oxygenation, complexity, or any goal. They were adapting locally to exploit available niches. It is easy in hindsight to treat these organisms as stepping stones toward more grandiose outcomes. In the reality of deep time, the road from chemolithotroph to photosynthetic cyanobacterium and beyond was neither inevitable nor directed. It was contingent on accidents of chemistry, competition, environmental shifts, and a prodigious measure of time. The planet listened. Microbial activity altered surface chemistry in ways both subtle and cumulative. Nutrient recycling increased local productivity, sediments thickened and changed composition, redox landscapes expanded. In turn, these changes opened new niches. Where iron concentrations fluctuated, new iron oxidizing strategies could prosper. Where energies from sulfide and hydrogen were abundant, communities clustered. Selection operated across nested levels. Molecules that catalyzed their own reproduction were favored. Cells that maintained advantageous internal composition survived. Communities that engineered stable microenvironments endured. From local persistence emerged system-level consequences. The tension between fragility and resilience becomes sharper when considering the environmental volatility of the time. Impact bombardment continued, volcanism remained unruly, and atmospheric composition oscillated. Yet microbes persisted through many of these perturbations by exploiting niches shielded from the worst of them. Deep vents, sedimentary refugia, protected tidal pools. Persistence, not perfection, was the evolutionary currency. Survival across repeated disruptions filtered for lineages and functional strategies that could endure or quickly recolonize. The result was the slow accretion of metabolic diversity and ecological complexity. There is an aesthetic truth to these episodes. The scale of agency changed. For eons, planetary change had been the province of molten rock and catastrophic impacts. With the first microbes, agency also resided in the chemical economies of tiny cells. Their collective action altered boundary conditions at the scale of oceans and atmosphere. The world acquired a new kind of author, innumerable, iterative chemistries encoded in self-replicating systems. They wrote slowly, in sediment and gas composition, in mineral precipitation and dissolved profiles. Their script was subtle, cumulative, and often concealed for billions of years. The narrative that follows remains humble in its claim. The first microbes were not progenitors of inevitable progress, but actuators of possibility. They demonstrated that, in the right conditions, chemistry can sustain repetitive, heritable processes that reshape environments. They inhabited the dark and the dim, the hot and the salty, the acidic and the neutral. They discovered, by trial and myriad error, ways to tap energy and carbon, to build boundaries, and to persist. Their descendants would diversify and, through a mosaic of new metabolisms and fortuitous innovations, eventually change the planet's atmosphere, climate, and surface in ways no single event could predict. If deep time invites humility, it also invites a peculiar kind of reverence. The first microbes were small actors in a vast theatre, yet their cumulative output was planetary. From the lowly oxidation of sulfide to the quiet production of methane, from sticky mats that trapped sediment to the slow compaction of organic matter into protosoils, they laid foundations. The planet's history after 3.8 billion years was, in part, the history of those foundations being built upon, overwritten, and occasionally erased. Life's early episodes were experiments written in shallow script, legible only to the patient readers of rocks. In the final measure, the creation of the first microbes answers a larger question about what it means for a world to become alive. Life did not arrive as a sudden flourish of complexity, but as persistent competence. The ability to harness available energy, to reproduce, to occupy niches, and to alter the environment in return. That competence multiplied across time and space, turning chemical possibility into ecological reality. The first microbes were the modest authors of Earth's new chapter, not loud enough to alter the sky in a single day, but industrious enough to change the chemistry of oceans and atmosphere across eons. They were the ancestors of all later life, the slow-handed artisans who, in their patient persistence, taught a planet how to remember. What if the first great revolution on Earth was not political or geological, but chemical? A change so quiet, so microscopic, that it began as a whisper inside the metabolism of single cells and ended by rewriting the very chemistry of the atmosphere. The idea is simple and staggering at once. Life learned to split water. For billions of years, the surface chemistry of the young planet had been defined by scarcity and reduction. Hydrogen-rich gases, ferrous iron dissolved in vast seas, methane wafting like a dim blanket. These were the currencies of early energy economies. Metabolism worked within those constraints. Then, in shallow mats and stromatolitic thickets that carpeted sunlit shores, a biochemical innovation spread. A complex molecular apparatus capable of capturing photons and using their energy to extract electrons from water. The waste product of that process was molecular oxygen. The organisms that pioneered this pathway, cyanobacteria or their ancestors, did not set out to change the world. They were simply exploiting physics and chemistry, folding together protein complexes and pigments into two cooperating reaction centers that, together, could move electrons uphill from water to carbon dioxide. Photosystem 2, the delicate catalyst that could yank electrons out of H2O, was an invention of improbable biochemistry. It required metal cofactors, precise geometry, and a cascade of redox steps tuned to sunlight. Those cells, in their billions, became oxygen factories. At first, oxygen was invisible as a planetary force. It bubbled away at local scales, reacted immediately with abundant reduced minerals and gases, and left little trace in the air. The oceans acted as a sponge. Dissolved iron seized the nascent oxygen and precipitated as rusty oxides, forming the spectacular banded iron formations, layered rust-red strata that would later be read as chemical testimony of a planet being oxidized. Those formations are not mere rocks, they are ledger entries in the planet's account books, recording a time when biological oxygen slowly overcame geochemical appetite. The narrative of oxygenation is not linear, but episodic. For long stretches, oxygen production and oxygen sinks were in rough balance. Then, as photosynthetic communities grew and persisted, sinks became saturated. The cumulative effect was not merely the oxidation of local minerals, but a rising partial pressure of O2 in the atmosphere, a threshold phenomenon in deep time. Around 2.4 billion years ago, the planet crossed a boundary later known as the Great Oxidation Event. The air acquired a permanent trace of oxygen. The chemistry of surface water shifted. New reaction spaces opened and old ones closed. This revolution had consequences beyond chemical bookkeeping. Oxygen is a reactive gas. It corrodes, it oxidizes, and it changes redox landscapes in profound ways. The rise of O2 transformed iron-laden seas into environments where iron minerals could precipitate and then be sequestered. It also attacked methane, the potent greenhouse gas that had helped keep the faint early sun from freezing the world. As methane was oxidized to CO2 and water, the greenhouse efficacy of the atmosphere declined. That change played a role in dramatic climatic perturbations, including prolonged glaciations. The Earth that had once been held warm by methane's blanket experienced intervals of global chill. Episodes where ice reached far toward the equator and the planet's thermostat was rewritten by biology. There was loss as well as gain. Oxygen itself is poison to many ancestral metabolisms. The microbial pioneers that had evolved for life in a reducing world found large swaths of their chemical habitats transformed. Extinctions at microbial scales, not singular apocalyptic events, but persistent displacement, reshaped ecosystems. Oxygen's arrival forced life to adapt or to retreat into refugia where anoxia persisted. In that brutal pruning, however, new metabolic possibilities emerged. Oxygen allowed more efficient energy extraction from organic substrates. Aerobic respiration began to outcompete its less efficient anaerobic counterparts wherever oxygen was available. More energy per carbon atom meant that organisms could build more cellular machinery, support larger cells, and, crucially, pay the metabolic costs of more complex bodies. The atmosphere's oxygenation also generated an ultraviolet shield. Molecular oxygen in the upper atmosphere interacts with solar UV to form ozone. This fragile, thin layer would later become a crucial gatekeeper, reducing the flux of sterilizing ultraviolet radiation that reaches the surface. Where ozone thickened, the energetic environment softened. Surface niches that had been deadly to fragile organic assemblies became less hostile. The combination of oxygen in the air and an ozone screen above it changed the rules for surface chemistry, for the stability of exposed biopolymers, and for the possibility of life moving beyond the protective hush of water. Earth began to breathe is more than an image. The coupling of photosynthesis and respiration generated diurnal and seasonal rhythms in gas fluxes. Day-lit production of oxygen, nighttime consumption by respiration and decay. Over geologic intervals, these rhythms scaled to planetary processes. Oxygen concentrations rising and falling, atmospheric composition oscillating through regimes controlled by biology and geology alike. Oxygen became a shaper, oxidizing minerals, enabling new metabolisms, carving niches for colonial and multicellular experimentation. That experimentation found its deepest leverage not in the atmospheric chemistry alone, but within the very cells that learned to exploit the new energy regime. The step from prokaryote to eukaryote, from small relatively simple cells to larger compartmentalized ones, was, in the geological ledger, a pivotal innovation. Eukaryogenesis appears as a composite event, an archaeal host cell, incorporating, retaining, and domesticating a bacterial symbiont. That symbiont would evolve into the mitochondrion, a tiny power plant that could extract vast quantities of usable energy from fuel via oxidative phosphorylation. Mitochondria provided an energetic return on investment that was orders of magnitude greater than what anaerobic metabolisms could typically achieve. With more energy available per genome copy, cells could tolerate larger genomes, more regulatory circuitry, and the emergence of internal membranes, cytoskeletons, and complex trafficking. Complexity, in part, was purchased with energetic currency. Endosymbiosis was not a lone event, but a mode of innovation that reconfigured cellular economies. The mitochondrial endowment was transformative. It permitted increased cell size, enhanced motility, and, importantly, the metabolic sophistication that supports differentiated tissues. When oxygen levels rose enough to make aerobic respiration both possible and advantageous across more environments, the stage was set for multicellularity. Multicellularity did not appear suddenly as a blueprint. It was a process, repeated, convergent, and experimentally plural. Across the eons, lineages experimented with collective life. Cells that once lived as independent units found advantage in sticking together. Greater resistance to predation, improved nutrient acquisition, division of labor, and better control over internal microenvironments. Key innovations recurred. Mechanisms of adhesion that allowed cells to bind, communication pathways that coordinated behavior across cells, extracellular matrices that provided structural scaffolding, and regulatory genes that could dictate differentiation and patterning. At the molecular level, the evolution of multicellularity leaned on an emerging toolkit. Adhesive proteins, often modifications of ancestral cell surface molecules, enabled forms of gathering. Cell signaling networks, kinases, small peptides, and receptor systems provided channels for cells to exchange state information. Gene regulatory circuits that could turn suites of genes on and off in a coordinated fashion permitted developmental patterning. Cells could now take on different fates depending on context. Development, in this sense, is a form of collective computation. It is a way for an assemblage of cells to process spatial and temporal cues and produce organized, functional morphology. Ecology pushed and pulled these innovations toward complexity. Predation, once rare, became a driver of evolutionary novelty. The evolution of motile cells that could graze on bacterial mats created incentives for prey forms to become larger or better defended. Armor and skeletonization began as local experiments in mineralization, often co-opting abundant ions like calcium. The production of hard parts set the stage for a fossilizable record, shells, spicules, and plates that would later register the sudden blossoming of body plans. Nutrient dynamics mattered, too. The oxygenation of oceans changed the availability and cycles of key elements. Phosphorus, iron, and trace metals were redistributed among reservoirs. Episodes of glaciation and thaw, weathering pulses from rising continents, and volcanic stirrings all reset nutrient availability. Where pulses concentrated nutrients, biological productivity could surge, providing energy and selective pressure for larger, more integrated forms. In essence, the planet's physical upheavals and the metabolic revolutions of life fed into each other. Geology supplied the resources, biology learned to use them, and ecosystems grew in complexity as a consequence. By the late Precambrian, colonies of cells had learned further degrees of integration. Experiments in body plans produced fractal mats, sheet-like organisms, and creeping quilted surfaces that exploited light, nutrient, and mechanical gradients. Some lineages developed the genetic and developmental architectures to produce larger, coordinated shapes, and these lineages produced bodies that cast shadows, stirred sediments, and began to engineer niches at scales previously unimaginable for microbes. The narrative from microbes to multicellular life is not a tidy ladder but a branching thicket. Many attempts failed. Many lineages retreated to unicellularity when conditions turned hostile. But incremental innovations accumulated. Energy budgets expanded, cellular architectures became more elaborate, and ecological relationships, predation, symbiosis, competition generated pressures that favored integration. Over time, the planet's biosphere changed not just in composition, but in tempo. Evolutionary rates accelerated in some clades, ecological interactions intensified, and the emergence of bodily complexity became a recurring theme rather than an isolated curiosity. The Earth's breathing, the interplay of photosynthesis and respiration, of oxygen pulses and sinks, thus became both cause and consequence of complexity. Photosynthetic mats pumped oxygen into seas and air. Oxygen enabled energetic metabolisms and protected habitats through ozone formation. Energetic metabolisms allowed cells to invest in structures and cooperation. Cooperation enabled bodies that could engineer environments back. The loop is recursive and cumulative. In the long view, the oxygen revolution and the rise of multicellularity are chapters of the same story. The planet's chemistry invited new biological architectures, and those architectures in turn remade planetary chemistry. Deep time shows this as a layered process of feedbacks, contingent events, and gradual thresholds. The emergence of photosynthesis did not instantaneously make the world habitable in the human sense. Instead, it opened a set of pathways, some fatal to older life forms, others generative for new ones. The result was a planet that, through the action of microscopic engineers, learned to breathe more richly and to support larger, more complex bodies. A world where the breath of single cells could, across billions of years, scaffold seas of living forms and, later, the bewildering diversity of multicellular life. What does it mean for a planet to become, in the fullest sense, alive? It is not a single invention or a heroic breakthrough. It is a long accretion of habits, interactions, and feedbacks that, over billions of years, weave isolated chemistries into coupled networks. On a world that had once been incandescent and hostile, the quiet persistence of chemistry found places to rehearse ever harder experiments until the rehearsals changed the set. Single cells, appearing first as marginal successes in hydrothermal chimneys and sun-warmed pools, multiplied their tactics, diversified their metabolisms, and, in a slow, stubborn choreography, learned to cooperate. From those primitive beginnings, the oceans slowly filled with more than chemistry. They filled with life. Imagine the oceans as laboratories in motion. For an eon, planktonic communities drifted where currents would take them. Some were simple photosynthetic microbes that skimmed surface light and exhaled minute puffs of oxygen as a byproduct. Others were chemolithotrophs, mining the planet's own rocks for electrons. Each lineage was a tiny experiment in energy capture, a series of metabolic choices written in the language of enzymes and membranes. Reproductive cycles meant replication, and replication meant selection. Over geological spans, selection favored robustness, more efficient energy capture, improved nutrient uptake, motility, and ways to shield sensitive chemistry from radiation, acidity, or heat. Then something like acceleration occurred. The fossil record, faint and sparse, nonetheless carries a clear pattern. Faunas and floras diversified rapidly in pulses and fits. The Cambrian is often invoked because it marks a spectacular blossoming of body plans, shells, segmented bodies, appendages that could grasp and dig. But the real drama began earlier and carried on later in waves. Multicellularity itself appeared independently many times, each emergence a different solution to a shared set of problems: how to exploit resources more effectively, how to avoid predation, how to stabilize an internal chemistry against external chaos. Cells that clumped and cooperated could specialize, some for feeding, some for defense, some for sensing the environment, and together those assemblies became bodies. Oceans transformed from dilute soups into dense, layered ecosystems. At the surface, mats of photosynthesizers created shimmering carpets, the productivity of which multiplied the flow of organic carbon through the sea. Zooplankton grazers evolved responses to light and chemical cues. Predators evolved mouths, hooks, and strategies for capture. Food webs lengthened. Detritus fell from the photic zone to the depths, became the fuel of benthic communities, then cycled back. Symbioses proliferated. Microbes living inside larger tissues, nutrient-exchanging partnerships between bacteria and eukaryotes, so that single organisms became ecosystems unto themselves. This expansion had planetary consequences. As photosynthetic biomass increased, so did the biotic drawdown of carbon dioxide. Carbon began to flow, not merely through rocks and atmosphere, but through living tissues that could bury organic matter in sediments, locking away carbon on long timescales. Chemical niches altered. Iron that once swam freely in reduced seas became precipitated and sequestered by biotic and abiotic reactions. Oxygen, first a local product, gradually accumulated where sinks were exhausted. The chemistry of oceans and air shifted. Climates changed in response. Life was not merely responding to planetary conditions anymore, it was an agent shaping them. When the first green colonizers crept ashore, the planet's skin changed again. Land was not won in a single conquest, but in stages of experimentation at shorelines, estuaries, and damp rocks. Microbial mats held sediments together, creating the first proto-soils. Lichens, part fungus, part photosynthetic partner, scraped minerals from rock surfaces, producing grit that mixed with organic matter to make a primitive soil. These early terrestrial engineers were small and unassuming, yet their collective actions created new habitats. Thin films of moisture, niches of shade, pockets of nutrient-rich detritus. They decreased erosion in some places and accelerated rock weathering in others, releasing phosphorus and other limiting nutrients into runoff that fed coastal ecosystems. The colonization of land required solutions to desiccation, support, and nutrient acquisition. Vascular plants, those that evolved internal plumbing to move water and nutrients and structural tissues to stand upright, were evolutionary innovations that paid these bills. Once lineage after lineage discovered rigidity and transport, plants could exploit vertical space, build height, and develop leaf surfaces that maximized light capture. Forests emerged from these experiments. Where soils had become thick enough to hold roots and water, trees took hold, and with them soil ecosystems expanded dramatically. Fungi intertwined with roots, forming mycorrhizal networks that exchanged mineral nutrients for carbohydrates. Arthropods chewed, decomposed, and redistributed matter. Microbes mediated nutrient availability in the thin, dark microzones of the soil. This greening of the continents rewired Earth's surface processes. Terrestrial photosynthesis drew still more carbon from the atmosphere. Forests sequestered carbon in woody matter and in soils rich with humic compounds. Vegetation changed albedo-dark forests, absorbed more solar radiation than bare rock, and modified hydrology. Transpiration from leaves fed atmospheric humidity, enhancing cloud formation and altering precipitation patterns. Rivers, now carrying heavier loads of organic rich sediments, delivered different nutrients to coastal shelves, and coastal ecosystems adapted to new food and chemical regimes. The planet's climates became more complex, with land-sea contrasts fostering regional circulations and seasonal rhythms increasing in amplitude and predictability. Ecosystems matured through co-evolution, a whispered, iterative negotiation. Herbivores pushed plants toward defenses, lignin, silica blades, chemical repellents. Insects evolved mouthparts to circumvent trichomes and toxins. Fungi adapted to break down refractory plant polymers. Predation drove arms races, better mobility, camouflage, and sensory organs. Each evolutionary step changed selection pressures across multiple lineages, propagating ripple effects through food webs. Where once a species' evolution would seem isolated, it became clear that life evolves as an interconnected web changes in one node, reconfiguring many others. With complexity came new modes of engineering. Reef builders, first microbial mats and later calcareous and siliceous animals, constructed three-dimensional habitats that magnified biodiversity by providing shelter, substrate, and microclimates. Burrowing organisms reworked sediments, influencing oxygen penetration into the sea floor and the recycling of nutrients. Biogenic sediments, limestone, chalk, and coal, recorded epochs where life's accumulation became a geological force. Fossil fuels, compressed and buried, were proof that life's productivity altered lithospheric reservoirs in ways that would only be read by later intelligences as archives of vanished productivity. Yet this story is not one of linear improvement. The planet's living fabric was repeatedly thinned and, in places, torn. Mass extinctions, episodes when many lineages went extinct or contracted dramatically, are part of the narrative. Some extinctions followed catastrophic external assaults, bolide impacts, flood basalt volcanism, abrupt climate swings. Others unfolded more quietly, driven by long-term changes in sea levels, nutrient cycles, or atmospheric composition. Extinctions were not failures, but rerouting events. They removed dominant groups, opened niches, and allowed radical radiations. The rise of new ecological strategies often followed these clearing events. Evolution, in that sense, is opportunistic and opportunely indifferent, capable of swifter novelty when systems are reset. Throughout these upheavals, resilience emerged as a defining characteristic of life on a planetary scale. Redundancy, many organisms performing similar ecological roles, prevented single losses from collapsing entire systems. Diversity buffered fluctuating conditions. When one lineage failed under stress, another filled the vacuum. Long-term feedbacks evolved between biota and environment. Vegetation maintained soils that held water and moderated runoff. Marine calcifiers regulated carbonate chemistry. Planktonic communities influenced atmospheric gases. Systems that might once have been fragile learned to store and reallocate energy and matter across seasons and centuries. These stabilizing feedbacks made certain states of the planet more persistent, but also made transitions, when they occurred, more consequential. The maturation of nutrient cycles, carbon, nitrogen, phosphorus, sulfur, was central to the living planet's character. Nitrogen began to be fixed biologically on a global scale, freeing photosynthesis from the strict dependence on abiotic sources. Phosphorus, weathered from rocks and cycled through soils and sediments, became the gatekeeper of productivity. Its local limitation shaped blooms and collapses. Sulfur and iron cycles, intimately linked to redox states and to microbial metabolisms, mapped across oxygen gradients and defined habitats from oxygen-rich surface waters to reduced sediments. Where humans look back, they find isotope records and mineral deposits that are signatures of these cycles, proof that life not only used elements but rewired their flows. Equally important was the emergence of behavioral complexity and niche construction. Animals did not merely adapt to environments, they modified them, building burrows, constructing reefs, altering vegetation through grazing and trampling. Such activities fed back on selection pressures, sometimes stabilizing ecosystems and at other times creating new gradients that favored diversity. Constructed habitats could create refugia during harsh intervals and could also serve as stages for new innovations. By the time the continents were cloaked with dense vegetation and the oceans crammed with diverse trophic layers, Earth had become, in an operational sense, a living planet. Its atmosphere carried signatures of its biosphere, its soil stored the memory of millions of years of organic labor, its coasts and reefs were theaters of constant experiment. But for all its fecundity, the planet remained contingent. Long timescales meant that subtle shifts, continental drift, orbital cycles, or a change in solar output could cascade through ecosystems. Gaia-like notions of homeostasis are seductive, but the reality was messier. Ecosystems could promote stability in some variables, amplify instabilities in others, and sometimes collapse in ways that were only restored by entirely different ecological assemblages. There is, in the long sweep, a humanly resonant aspect to this process. Observers constrained within a single lifespan can hardly perceive the slow accretion of niches, the patient work of soil formation, the gradual diversification of sensory systems. Yet those processes are the very things that make a planet comprehensible and habitable. The shift from watery microbes to carpeted continents and bustling seas was an elaboration of inheritance. Genetic, ecological, and geological. Time served as both teacher and filter, allowing repeated trials, amplifying successful strategies, and extinguishing ephemeral dead ends. To narrate the living planet is to insist on scale and interdependence. It is to notice that a leaf's surface chemistry is part of a planetary negotiation. Light intercepted there reduces CO2, feeds a fungus in the roots, alters cloud patterns, and ultimately participates in climate. The tiny is coupled to the large in ways that are not metaphorical but causal. The emergence of forests changed river chemistry and, across epochs, shaped which minerals were available to organisms in distant seas. The world that had once been an indifferent ball of silicates and metals now became a self-referential system, where life's processes continually reconfigured the environment that, in turn, selected for new life. And yet, after billions of years, the living planet still retains a fragile humility. Complexity does not immunize a world from catastrophe. It only changes the forms in which catastrophe is felt and healed. The tapestry of life is dense, rich, and resilient, but its threads are braided through contingencies. The timing of oxygenation, the advent of terrestrial roots, the arrival of new predators. Each thread might have been otherwise. That realization is both unsettling and liberating. It asks of any observer a modulated awe, admiration for a system that produced oceans of life from a furnace of rock, combined with a respect for the precarious balances that sustain it. In the end, the phrase living planet is not a metaphorical flourish. It names a process, a planetary body in which matter and energy organize across scales, where history is stored not only in rocks, but in genomes, and where feedback loops between organism and environment generate emergent behaviors. From single-celled whispers to forests and reefs teeming with interlocked communities, Earth became less a stage for life and more a co-author of it. The story is ongoing. The planet remains alive in the sense that it continues to change, to remember, and to host the restless experiment that is life. What does it mean to look at a green planet and not take it for granted? What does it mean to stand beneath a canopy of leaves and hear the chorus of insects, birds, and wind, and to sense that every note of that chorus is an answer to a long list of improbable questions? These are not rhetorical flourishes. They are the last, weighty observations in a story of relentless contingency. Earth's emergence as a world clothed in green was not a single victory lap, but the cumulative consequence of countless small passes, near misses, and fortunate timings. To say the planet became alive is to admit to a slow choreography in which chemistry, rock, water, light, and, very late in the sequence, living systems learned to dance together without stepping on one another's toes. The panorama is both intimate and impossible. From the molten furor of accretion, through the rearrangement of metallic cores and the birth of a satellite from planetary violence, to the patient settling of steam into oceans, each stage could have folded differently. Slight variances in mass, angle of impact, abundance of radioactive isotopes, or the timing of volatile delivery would have rewritten the odds. A world with a feeble dynamo might have lost its atmosphere to the young sun. A slightly more massive bombardment at the wrong time could have boiled away nascent oceans. A different orbital geometry could have let seasons slip into erratic extremes. The Earth that became green represents one path through a forest of near-infinite forks. This is the first point the voice in the story insists upon. Contingency is not merely a quaint philosophical idea, it is the operating system of planetary destiny. Chemistry does not guarantee biology. Physics provides constraints and opportunities, but within those constraints, randomness and timing determine which experiments proceed. The planet's script is less a single authorial act and more a palimpsest of many hands, each writing, erasing, and rewriting. The green world is therefore a testament to the long patience of processes that merely needed time and not too many fatal interruptions. Time itself becomes the scale of wonder. 4.5 billion years is an infuriatingly large number, one that shrinks the human lifetime into an instant of a blink. When the narrator metes out that duration, it does so by analogy, a human heartbeat compared with the slow grind of continental drift, a single lifetime against the patient accumulation of soil. Those metaphors are necessary because the mind craves footholds, but there is a sharper truth beneath them. Evolution is not an upward ladder, but a vast stochastic search through a space of possibilities. It requires repetition, failure, and occasional success. The oceans and crust offered the repetition. The vents, pools, and tidal flats were the studios where trial and error could be rehearsed. The magnetic shield afforded the luxury of time by protecting volatiles from premature loss. The green expansion is legible in layers. First come pigments in microbe mats, small biochemical devices that harvested fragments of sunlight and slowly released oxygen as a byproduct. For epochs, that oxygen meant nothing visible. It was immediately sequestered in reactive minerals. Then, in a planetary ledger, the oxygen signal ratcheted upward and rewrote chemistry. Iron precipitated, methane declined, and the climatic thermostat shifted, sometimes violently. Once a threshold was crossed and an ozone layer accumulated, the surface chemistry softened. UV flux reduced, new niches became navigable. These steps were neither inevitable nor deterministic. They were slow pushes that, given slightly different initial or boundary conditions, may not have happened or might have happened in a different order, producing a planet with a habitability that looked foreign to what humans now know. Along these lines, a speculative whisper belongs in the narrative without becoming a distraction. The possibility that other forms of complexity might once have flickered and been erased. Deep time does not guarantee the permanence of any architecture. Geological recycling is prodigious. Plate tectonics buries and remakes, impacts and volcanism reset. If a technology-bearing society had arisen and vanished hundreds of millions of years ago, its artifacts would likely be ground to powder or subducted into the mantle long before human eyes could find them. The story of a green planet includes this epistemic humility. Absence of evidence is not evidence of absence in timescales that reforge the very records that could testify to past intelligences. That speculation is not an invitation to fantasy, but an admonition to modesty, recognition that the geological archive is both generous and selective. A second stronger point the narrative returns to is fragility folded into resilience. Life reshaped Earth profoundly. It altered atmospheric composition, sculpted soils, and redirected geochemical flows. Yet those same processes introduce dependencies. Forests sequester carbon, but their destruction releases it back into the air. Coral reefs build habitats while being exquisitely sensitive to changes in temperature and acidity. Biotic systems create feedbacks that can stabilize and destabilize. The green planet thrives precisely because its living systems form networks. Mycorrhizal webs under forests, planktonic cascades in seas that buffer against small fluctuations. But these networks also accumulate vulnerabilities over long intervals. The record of mass extinctions is a cautionary chapter. Life is transformative, but it is not invincible. When the narrator imagines the perspective of a human standing under a forest canopy, there is a deliberate emotional tilt. There is a sensation of humility, a vertiginous recognition that the pigment in leaves and the scent of soil are the outcomes of patient, improbable processes. There is gratitude, not in a moralized sense, but as an aesthetic response, a feeling akin to awe at a work of art created not by a single hand, but by a host of invisible artisans over deep time. Yet that same vision carries a sober sense of responsibility. To walk in a green world is to share a stewardship that emerges from the realization of fragile contingency. The biological and geological balances that sustain forests, rivers, and soils are the product of a narrow corridor through history. The narrator insists, too, on the necessity of scale translation. Modern technological societies often act as if the planet is an inert resource to be optimized on short timelines. Deep time rewires that instinct. Processes operating on millennial and million-year scales, soil formation, carbonate accumulation, silicate weathering, are slow accountants. Human actions can alter their trajectories in ways that manifest across centuries and millennia. Conservation, then, is not merely a sentimental holding on to a landscape. It is a recognition that the biosphere's capacity to self-regulate depends on the continuity of processes that humans can disrupt far more quickly than they can repair. A speculative documentary voice must also grapple with moral language while remaining scientific. The narrator refuses to moralize in simplistic terms. Earth did not do anything right, but it draws human-scale implications. The realization that life's flourishing is contingent invites a politics of caretaking rooted in humility. To speak of stewardship is to acknowledge that the present is an outcome of rare luck and continuous geological generosity. It is therefore a choice to pass on a similar opportunity for future biotic experiments. This is not an imperative couched in divine authority, but an ethical corollary of understanding. When knowledge reveals fragility, prudence follows naturally. There is a final, quieter theme to the closing pages: the role of narrative itself. Humans, the species that now reads this story back through instruments and fossils, are exemplary narrators. They reconstruct deep pasts from scattered hints and make meaning from fragments. That act of reconstruction is itself a continuation of the planet's habit of building complexity from information. Rocks carry isotopic signatures. Sediments preserve layers. Genomes whisper evolutionary histories. What humans do with those whispers, interpret them, learn from them, and, perhaps, change their own behavior, becomes another link in the chain of causation. The story of Earth's greening is, in that sense, also a story about attention. The more finely a species can read its planetary conditions, the more capable it becomes of acting with foresight. The narrator draws attention, too. to the aesthetic axis of wonder that runs throughout the tale. There is a kind of joy, an almost childlike delight in imagining cyanobacterial mats unspooling sunlight into oxygen, vents constructing mineral chimneys that double as reaction vessels, and early eukaryotic cells experimenting with internal compartments like inventors playing with new tools. This joy is not an escape from sober facts, but their companion. Deep time scale can be terrifyingly indifferent. It can also be a source of beauty because it reveals processes that patiently accrete complexity without hurry or judgment. And so the narrative returns to the beginning with a twist. The world observed in green did not have to become green. At countless junctures, it might have gone silent. It might have lost its volatiles. It might have been sterilized repeatedly by impacts or stripped by stellar winds. It might have cooled into a frozen desert or baked into an unbreathable pressure cooker. Each of those alternate histories is a ghostly possibility carried on the physics of chance. That Earth did not become any of those alternatives is not a cause for triumphalism, but for careful humility. The present is a fragile statistical outcome, a beautiful concatenation of improbable events. In the final scene, the narrator does not stage a crescendo or issue a call to arms shouted at a stadium. Instead, the voice softens into an invitation to listen. To look at a green planet is to register deep time patience and punctuated contingency. It is to acknowledge that the ability to host complexity was bought in the coin of rare accidents and long steadiness. The appropriate human response is not merely pride, but stewardship, an ethic built on the knowledge that the future depends on continuing processes that have been assembling favorably for billions of years. A green world is an argument against complacency. It is also the planet's greatest gift, the demonstration that, under some arrangements of matter and energy and chance, chemistry can become history, and history can become a canvas for ever more emergent forms. The story closes, not by denying the depth of unpredictability in the cosmic script, but by cherishing the narrow bridge that allowed life to cross from possibility into persistence. Humanity, and all other living things that now share this planet, exist in the aftermath of that bridge. They are inheritors of an immense uncertain legacy. The last line of this chapter, quiet, almost recusant, reminds listeners of scale and gratitude. They live on the miracle of 4.6 billion years of evolution, a miracle that is not magic, but the patient outcome of slow chemistry, hard physics, and a prodigious measure of luck. To witness the green is to be both small and intimate, both accidental and responsible. The planet's long and improbable journey from molten rock to teeming biosphere is not merely an origin myth to be admired, it is a charge to that smallest voice of agency left in deep time. The human capacity to see, to understand, and to choose how to act in a world that, against astronomical odds, learned how to keep itself alive.